Yes.
All right, great. So, um, how's everything today?
Um, very slow.
Yeah, three. Okay, well, our break ends today, so tomorrow I'm going back to teaching regular classes. So, yeah, good thing you
Mm-hmm.
caught me today for the 3 hour lesson. So, okay, let me just check. Am I streaming yet? Yes, I am. All right. So let me just open a few papers here. So we're basically done with what did we do last time again? Let me check. Okay, which one was it? CJ. Okay, I'm just looking for the board from before. All right. Uh, okay. Okay, so we basically finished the whole question on paper 3 on 2016, I think. Right? So today we're gonna start with 2021. Okay, 2021 papers. Um, okay, okay. Hold on. Let me just get all of this ready. Easy, easy. Okay, paper two. Oh, 2021 doesn't have a paper three, so we need to go a bit earlier on that. Okay, unless you want to redo the ones you've already done in class. Do you want to do that?
Sure,
All right, sure. Okay.
sure.
Let me just open those then. Okay, 2022 then. Let's do the latest one, 2023. The latest one we have access to. Okay. Physics. Paper, paper three. All right, and here. Okay. So by the way, I want to go use a new board for today because the last one it's getting pretty full, right? So
Yeah.
okay, so I'll just uh I already have a new board open. I'll just share that with you now, and then we can start while everything is loading up here. Uh, where is it? It's here. Okay, so I think everything else is. That's strange. My view looks very different here. Hold on. I'll just send it. I'll just send the message to you. I'll just send the link to you right now. Hold on. All right. There we go. Okay. So there's the new link. It's been shared with you on the chat box.
Okay, thank
All
you.
right. Great. So let's. Okay. Let's do paper three first, and then let's again go through how to answer that. Okay. Uh, paper three. Here we go. All right. Just to be sure, I'm gonna copy and paste the very first question on the data analysis section. Okay.
Wait, can you share your
Oh
screen?
yes, thank you for reminding me. All right, let me do that right
Thank you.
now. There we go. Okay, so should be okay now. Let's go through the paper. Okay. All right, just want to make sure. Have you done this particular question yet? Where this one, where you have a ball bouncing off a pressure gauge like this?
Mr. Dennis, you're not sharing your screen.
Oh, am I not?
No.
Hold on. Yes, okay. Thank
Okay.
you. All right, there we go. Have you seen this yet?
Yes, but I forgot.
Okay, so let's go through this. Let's go through the answers here again. Now, the first question here was this. It's basically asking you to state one variable that needs to be controlled. So give me one variable that needs to be controlled in this investigation.
I think the sensor,
Mm-hmm. Okay.
because usually like our school they always tell us to use the same like sensor because everyone has a different uncertainty or something.
Okay. Well, that's one way of doing it. But remember, the sensor is not a variable. The sensor is
Oh,
an instrument. When you see the word variable, it must be a measurable quantity. It cannot be an
so the
instrument. Okay.
pressure
Gauge.
pressure god gauge
Gauge. Okay.
meter.
Um. Okay. So again, what would I say? This should be a measurable quantity. Okay. The pressure gauge, again, the pressure gauge is not an instrument. Okay. So never answer an instrument
Hmm?
here. Never answer.
So
Uh,
pressure gauge is a variable.
yeah. No, the pressure
Okay.
gauge. Okay. Actually, when you say gauge, it's the same as saying gauge meter. So you could just say pressure instead. Okay.
Okay.
Material or instrument here. Okay.
Hmm.
Okay. So, um, however, you cannot use you cannot use pressure here. Again, you cannot use pressure here. Okay.
Okay.
Why? Because you are investigating the effect of pressure on the force. So these cannot be controlled. One of these must be the independent variable and the other must be the dependent. Cannot be the controlled variable. Okay.
Hmm.
Okay. So try again. Don't say pressure here. Give me another answer.
The wait 1 second. Let's see. Sensor's instrument. The
Mm-hmm.
gauge is measurement.
Mm-hmm.
The ball.
Okay. Something about the ball cannot be the ball itself. Yeah.
Oh, the ball's. What is it measuring exactly? Maximum force the ball.
Mm-hmm.
The
Okay.
ball's um size,
Size.
bounciness.
I wouldn't say size in this case. I don't think you'll get marks for size. Okay. Um. Okay. But the idea is correct. You can use size, right? The problem with the word size is it can mean volume. It could be mass, right?
How about the ball's mass?
Okay, that's gonna work. That's gonna work. Okay. Now, however, I'm gonna say something now. Okay. Never just say mass. Mass by
Mhm.
itself is wrong. You have to say the ball's mass is correct. Yeah. Why? Because when you say mass, the main idea here is if you say mass and nothing else, you're not qualifying what mass you're measuring. Are you measuring the mass of the ball? Even though it's pretty obvious, you still say the mass of the ball because if it's not clear, somebody could misinterpret it as saying the mass of the pressure gauge meter or the mass of the force sensor or whatever.
Mhm.
You get the idea? So you have to say the ball's mass in this case. Okay. All right. Okay, I'm now looking at the marking scheme, and yes, that's one of the acceptable answers. Any parameters about the ball itself will work. Okay.
Mhm.
Now one thing that I could add here that is a possible answer. So this could be mass, whatever of ball, right? Of the ball. This could be the what else? This could be the um temperature, right? Temperature. Even though it's not normally thought of, it's possible. It could be the size, in this case, the radius of the ball. So size can be radius can be size, right? It could be also the drop height. You could also say the drop height, right? What else do we? Yeah, drop height would be um another possible answer. So all of these would be possible answers here. Okay. The most obvious one that most students will probably say is the mass of the ball. But yeah, so that's fine. All right, let's move on. Next question. Okay, this time around, the data has been collected and you're given a table right here. Okay, there's your table and some questions. Okay.
Mhm.
Okay. So, let's read that. Let's read that first. So the student has collected the following data. You have the pressure gauge measurements, delta P in kilopascals, and the maximum force in newtons. And there's a hypothesis that F max is proportional to delta P. Okay, which two
Oh,
date? Okay, so how do you do that? Only using the two data points. Which two data points does not support that hypothesis?
oh, so there's
Mm-hmm.
two data points that don't follow it.
Yeah.
Okay, then I'll start with 10.
Uh-huh.
To, can I do like 10 divided by 108?
You can do that. You can do it the other way around. It doesn't matter. What matters is you do something with the numbers, right?
Mhm.
Okay, great. So you're saying that. So you said, so let's just do that in
Wait,
order. 108. Then what do you do? Do you multiply or divide? Because they're
uh,
directly proportional. What does that mean?
I think they divide them
Yeah,
because y, oh, y's over 1
yeah.
then.
So F max. If we do that in equation form, that should be equal to some constant k times delta p, right? So in other
Yeah.
words, F max over delta p should be a constant. And this is what you're going to check one by one. So, but
That's
if you
pretty
do it the
constant.
other way around, if you do it the other way around, it's still going to give you a constant, right? Okay, so
Mhm.
if we do this, okay, what do you do? You simply divide one by the other. We get, in this case, we'll get 10.8. Then the other one, I can already see I can already see that the second one won't match, right?
Mhm.
Okay,
I think I messed up.
okay, okay. Then next one. Okay. Now, it just says you use two suitable data points, right?
Mhm.
Okay. So which data points would you be using in this case? Once you finish going through all of it, what do you do?
That's a good question. Um, can I use 20 and 30?
20, and 30 already you can use, right? Um, okay. Now I'm gonna give you a clue here. When we say two suitable data points, you want these 2 points to be as far away from each other as possible.
Mm. Okay.
From each other as possible. Okay.
Mm.
So which ones would be the best?
Um, preferably like either 60, 70, or 80.
Uh-huh. Now I would personally use 80 and 10 already.
Seven, oh, oh, 80 and 10.
Yeah.
Wait. How do you do that?
Okay. First, yeah, you do. I'm just gonna do this. I get this 10.8 here. Then I'm gonna do this right here. What's gonna be 220 divided by 80? That's gonna give us 2.75,
Mhm.
right? And then what you do here next is you compare the values. Remember this thing that we just wrote here, that taking the ratio should be a constant, right? But do we get a constant? Do we have the same, excuse me, do we have the same value for the two data points we chose?
Same value?
Do they
No.
have the same value? They don't, right? Or at least it's not even close to being similar,
Yeah.
right? So in this case, okay, first data point, uh, constant of, I'm gonna write it like this: 10.8 is not the same as the what's that? The eighth point, right? Which is 2.75. Not even close, right? It's not the same or close. Uh, so what does this mean? This means that this initial hypothesis is not correct. So F max being proportional to delta P is incorrect. That's it. That's all you have to say here. Okay. So again, whenever you're comparing data points, you go to the two farthest points as possible. That way you can really see if there's a um, direct relationship or not, depending on what you say. Okay.
This is what it is.
Go ahead.
I've been trying to log into the Zeit board,
Okay.
but it's like not working for some
Okay.
reason.
Hold on. I will.
Okay, so if it's proportional, the values have to stay the same,
Mm-hmm.
right? It's
Mm-hmm.
like
That's correct.
190 divided by 10, and then 1,900 divided by 100. It
Right.
will equal the same.
Mm-hmm.
Okay.
Okay. I'll try that again. This should be. This should be. Let's change the settings real quick.
Thank you.
Okay. Let me just share that with you again, just in case I messed up the link. How come the link's different? All right, try that again. See if this works.
Thank you.
I've deleted the previous link.
Okay, it works. Thank you.
All right, great. Okay. Let's continue then. Uh-huh. Okay, what's the next question? Okay, this time around, there's a new. Okay, I think I better hold on. Zoom out first. Okay. So the next question now, the student has proposed that there's a new relationship and okay, and came up with a graph like this. Okay. So in this case, before we answer any other questions here, Okay, there we go. All right, so let's do that and zoom out a bit. Okay, so you now have this particular graph. So before I ask you the question here, do you think that this is already suitable as a linear graph, more or less?
Yes.
Yeah, okay, more or less, this is a suitable graph already. So in this case, the new proposal, the new hypothesis is now correct. Okay, so here's the first question. State the unit for k, and
I
okay,
could use the tables numbers, right? Yeah.
yes, yes, you can. And
So
plot on the
F3
graph the
is
position of the missing point of delta P of 40 kilopascals. There's a missing point.
40.
Hmm.
Sure.
So you have to do two
That's
things.
not that bad. 170. Okay, I'll write that. Um, wait, what? Where did you put it on the board?
Okay,
It didn't. Wait, it's. I don't have like a view point of view. I don't
that's
think I
weird.
have editing access.
Okay, let me double check that. You should, let me check the,
Oh, wait. Do something
you're
again.
not connected right now to
Okay,
the
it
link.
works. It works. Oh, sorry. I clicked. I think they updated because I clicked the link
Uh-huh.
and it's just.
Let me try that again.
It didn't let me. There was a button that said open, and then I opened it, and now I can like edit, but I can't see that graph.
Okay, hold on.
It's weird.
That's weird.
The only thing I see was the table
Mm-hmm.
and the thing from the question from before.
Okay, hold on. Okay, let's, I'll share the link again. It, I see, I think that every time I write something on it, it changes the link. So I'm gonna delete the other one again. Let's try that one more time.
Okay, I see it.
Mm-hmm.
Um, okay, I'll draw the point.
Okay, go.
But the unit is divided by. Wait. I have to look at the table, right?
Mm-hmm. Okay, I'll give you a clue for pressure, yeah? So again, pressure is force per unit area. Okay? That's the only clue I'm gonna give you.
Pi r squared. Force per unit area.
Uh-huh. But remember, you're only dealing with units. You don't really need to think of formulas for areas or anything else. Just think of the
Mhm.
definitions, and then from the definitions, you try to go through, um, yeah, just go through how that's done. Okay.
Mhm.
Anyway, I'll give you one more clue. I want you to look on the axes. That should already tell you what units you should be using.
Yeah, so it's like 30 times 10 to the power 5 divided by whatever.
Okay.
Hmm.
All right. I think I'll go help you out now. Okay. So first of all, let's take
Yeah.
a look at here. That's kilopascals, right? Right.
Mhm.
So that's gonna be kilopascals. Just redo that. Kilopascals like that, and then I'm going to for pressure, right? And then for force, you get um Newton. But this is force cubed, so that should be Newton cubed, right? So just go back here. Pressure equals force over area. So what's the unit for pressure? It's right there. It's going to be in kPa, right?
Mhm.
Right? And then, okay. Before that, I forget. So let's go back to the formula that's right here. It says it's right there, right? So F cubed, F max, right, equals K delta P. So what do you have to do? You just rearrange this equation so that you have your K there as your subject. So that's going to be F
Mhm.
max cubed divided by delta P. That's all you have to do now. Now, what is, um, so, okay, I'll just do this here now before we continue. So this means 1 over the pressure, or let's put the delta in there, is going to be equal to the area over the force, right? Okay, so all I'm going to do now is rewrite that. So rewrite this thing with this in mind. Okay, so what's this going to be equal to? Your K will be equal to F max. Well, I'm just going to write F now, times 1 over is a F cubed here rather, A over F. What happens? Your F cancels out partially. So finally, you get your K should be in F squared per times A, times area, right? Okay.
Mhm.
Now, having said that, what are we gonna do? What are we gonna do now? This is 10 to the 5. So, what's um okay, I saw you pop in and then go right out again from here in the board.
I didn't go out though. I'm
Yeah.
still here.
All right. So
It's
what do
weird.
you do now? So anyway, let's continue there. So K equals F squared A. F is what? Newtons, right?
Mhm.
So and area would be square meters.
Yeah.
So K should be in Newton, then square meters. But your Newton there is squared, so this also squared. That's your unit. And that's the
Hmm.
answer. Okay, that's already the answer. Okay. Now, um, the idea here is this is good enough. We don't normally wanna go all the way to base units in paper 3. It's usually done in paper 2. Going all the way back to base units is done in paper 1 and paper 2. Paper 3, just leaving it like this is totally fine. Okay. Or okay, so this is one possible answer. Another possible answer is newtons would be kilogram meter per second squared, but it's squared already, so that's gonna be squared here, and 4 here, then meter to the squared, right? So that's gonna become kilogram meter to the 4 per second raised to 4. That's another possible answer. Okay, another possible answer here is you just keep this. This is gonna be Newton cubed per kilopascal, and that I think that's the fastest answer here. The safest answer is to do the first one, not all the way through, but not like just putting it all together. So this would be again noting that this is the safest answer. Okay.
Hmm.
Okay. All right. Okay. Now let's go to part 2. Plot on the graph the position of the missing point of the delta P value of 40 kilopascals. So you have to go back to the table. Oh, my kid's here to say hi. Say hi.
All right.
All right. Uh,
Okay.
okay.
Um.
So going back table, I'll just put the value for 40 kilopascals here. Okay. Put it here, right there. So again, for 40 kilopascals, the value of the maximum force is 170.
Yeah. Oh. Okay. So we use the equation.
Mm-hmm. Yes, we use the equation given to us here.
Find k or no.
Actually, no need to find k. Never
Oh,
mind. Yes. No need to find k in this case. You just actually plot the value. If you find k, then yeah, you just basically.
uh, I don't know. I've just been like so confused here. Like it says 170, but like when I'm
Aha.
looking at the other data points and where they're plotted.
Because remember that this is in newtons, not in this is just newtons, right? This
Mhm.
is already in kilopascals. But look at the graph again. Look at their equation. Let me just scoot that down a bit. So again, look at the equation right here. It's
Mhm.
f cubed, right?
Yeah,
So what do you need to do with that value earlier of 170? What do you need to do with it?
times 10 to the 5 and
No,
then divide by the Newton cube.
no. It's f cubed. You literally cube this value in your calculator and use that value in the graph. In other words, let me
But
show that
isn't it already cubed?
it's not yet cubed. Remember, this is your raw data of 170.
Oh, yeah, yeah. It does not say cubed. Oh,
There we go. It
cool.
doesn't say cubed yet. It's just in newtons.
Wait, if I draw, will you see it? Wait, okay, I'll draw it.
Yeah, go ahead, try it out. See if I can see it.
Oh, wait. Okay, wait. Okay, I drew a point on the graph.
Mm-hmm.
Can you see it?
No, I don't.
Oh, I drew it right below 50 on the
Okay,
y-axis.
that should be fine. So let me just do that real quick here. Somewhere here, right?
Yeah.
Okay, that should be fine. Uh, if of course on the paper you're gonna have a bigger space. Can you just tell me the value that you would actually draw that on?
4913,000.
Okay, correct.
Or 49, 49.
49. You're gonna put that to 49, correct? Okay. So I'll just note this here. This should be 49, specifically 0.13 if you can, right? Okay, great. So that's at 40 and 49.13. All right. Next question is this. Okay. So here, this time around, you're given the percentage uncertainty in Fmax. Okay, and then the error bars for 10 kilopascals and 80 kilopascals are shown. For the first one, calculate the absolute uncertainty for 30 kilopascals of delta P and number of significant figures to your answer. Okay, I'm gonna. Okay, you tell me first what you need to do here.
Uh, Absolute uncertainty.
Mm-hmm.
So we find the error bar going one direction, like above,
Mm-hmm.
either above or below
Mm-hmm.
of both
Mm-hmm.
80 and 10.
Yeah, but this time you're
No,
focused on 30.
30.
Mm-hmm.
The error bar for 30.
Mm-hmm. So you're looking for the error bar at 30. So let's go back to the graph real quick. So which one are you going to be interested at? This point.
Mm-hmm.
Okay.
Yeah.
Okay. So what's going
Uh,
to be the uncertainty in oh sorry. What's the uncertainty in F max? Yeah, in
5%.
F cubed rather, in F cubed.
Oh, F cube.
Mm-hmm.
15%.
Correct. It's going to be 15%. Uh Care to explain why?
because uncertainty is added, not multiplied.
Mm-hmm. Okay. Um, Uncertainty will be 15%. Okay. All right. Specifically, if we say that, that should be delta F cubed over F cubed like that. But yes, it's going to be 15%. Okay. Why again? That's
Wait, why is it
because
delta f cubed over f cubed?
it's a percentage
Yes.
uncertainty. So you always express that uncertainty relative to the actual value. Because again, saying delta F cubed only is absolute uncertainty. Okay. Okay. So this would be
Uh,
relative. You can say this is relative or percentage or fractional uncertainty. All these terms mean the same thing.
so I always have to put fractional uncertainty.
Not necessary. It depends on the problem. Here, because you're given the percentages here, you have to express it as the percentage or as the fraction like this. Okay. All right. But
How do I
having
know
said,
it'll be delta f cubed? Sorry.
okay. So, sorry, say the question again.
How will I know if it's delta f cubed?
Well, you go back to the graph. Here in this graph, it's already mentioned on the y-axis that it is already f cubed, right? So do you
Mm-hmm.
need to do anything special with this number or do you use it as is?
As is.
As is, okay? So what's that? 30, that reads to what?
40.
40. All right, so let's put that up, okay? So what's f cubed here? F cubed is equal to
30,
30.
40, 40.
Right,
Wait,
right. It was
yeah,
30. It was
30.
40. X
Wait,
delta p was 30, right?
yeah.
And then x cubed is 40. All right. So what do we do now?
Use that. We don't use the equation.
Mm-hmm. Yes, but which equation?
The f cubed equal k
This thing.
delta p.
Yes, correct. You use this now. Use this. Calculate for. Now it's now
K.
saying you're looking for the absolute. This is now we're looking for delta f, right? What's delta f equal to? So as you said, we use. We'll just do this here now. So we'll use delta f cubed. Delta f cubed over, in this case, 40 is equal to 0.15. I'm going to change that to decimal now. So that should be pretty straightforward, right?
Wait. So the equation finds delta f.
Mm-hmm. So we're looking for delta f. So absolute
So the
uncertainty
k.
here would be delta f cubed. Okay.
Mhm.
Okay. The k, we don't really care for the k right now because we're not asked to do it yet. We were just asked to look for the units. Okay.
Wait. So 0.15 is 15%. But what
Yes.
equation is this?
So again, we're just looking for delta f cubed. So what do? We want to move that 40 to the other side, right?
Mm-hmm.
So
Times 40.
0.15
40
times
times
40,
0.15.
and that's going to be
6.
equal to 6. But okay, here's the thing.
6 cubed.
No, it's
No.
your
Never mind.
f cubed is already 6. All right, let me rewrite that.
Yes.
Okay. So in this case, f
Oh, okay.
cubed delta f cubed is already equal to 6, and that's what we're looking for. Okay. But it says here that we need to state our answer to a correct number of sig figs. So how many sig figs should we have? 1, 2, or 3?
1.
1. Why 1?
Because there's only one digit
Not quite. It's
as
because this has, because this has
one suffix.
1 sig fig, right? So this means 6 must also have 1 sig fig.
Mm-hmm.
So that's already done. 6, not 6.0, not 6.00. That's done. That's 3 marks. Okay, I'm making sure that this is correct on the mark scheme. Okay, yeah. Okay. Now, I
I
just
don't.
want go ahead. I just want to go
Sorry, I know
through. Sorry, you go ahead.
I know the uncertainty is 15%, but
Mm-hmm.
I'm not sure if I can ever come up with delta f over f cubed.
Mm-hmm.
Delta f
Now,
cubed over f
now,
cubed.
in case you wanna. Okay, let me open the data booklet here again. Hold on, yeah. Hold on. Okay, but anyway, in case you can't remember, this thing is still in the data booklet, specifically in um topic 1.2. Okay, so which one do you use here? Again, you just have to remember the annotations here that we have. I'm gonna annotate this again here. Okay, so
Oh,
this is in the
the
booklet.
second one.
Yeah, so you could use either the second or the third one,
Yeah,
right?
but this one's a graph, so
Mm-hmm.
the top, the second
Right.
one makes more sense.
Mm-hmm. But yeah, but anyway, either case, it doesn't really matter which one you use because they're similar. They're gonna be the same thing, right? So remember, this is
Mm.
absolute uncertainty, okay? And these two would deal with percentage uncertainty, okay?
Mhm.
Or fractional. What else?
Wait.
Fractional or relative, okay?
Okay.
Percentage, fractional, or relative,
Hmm.
okay? So this should give you a big clue. Also, this part, it's delta y over y. It's
Oh,
not just delta y, okay? All right.
yes.
So let's move on. Any questions before we move on?
Does delta y mean like the uncertainty?
Delta y is the uncertainty. Yes.
Okay, that means delta a and delta b is also uncertainty, but
Yes.
delta
Absolute.
y is the absolute uncertainty.
Yes. Correct. Okay.
Okay.
So let's just put that there. So again, if it's just delta, then it's absolute. If you see a fraction, that kind of gives you the clue, right? Because if it's a fraction, that gives you a fractional uncertainty.
Mm-hmm.
All right. And fractions can be converted to percentages. Okay.
Yeah.
All right. There we
Wait,
go.
wait.
Okay. Okay.
So so every delta sign or delta y or delta any letter
Mhm.
is an uncertainty.
Yes.
Okay. Oh, that's why it's just a. That means it's either y,
Uh-huh. All
for
right.
example, 40.
Yeah.
Okay.
Yeah. Now, another thing that could help you out here is the word uncertainty itself. Uncertainty means you're not sure. That means you have a range of possible values, right? If
Mm-hmm.
you have a range of possible values, then that means there must be a difference between the minimum and the maximum. That's why we have delta.
Mm-hmm.
Okay. So,
Could it be any of them?
mhm. So again,
Okay.
let's just put this here. So delta y means there's a range of possible values. And that's exactly what uncertainties do, right? Because of the fact that you cannot have a perfect measurement.
Mhm.
Okay. In fact, just a little bit, this is a little bit TOK, but I don't think it's discussed a lot. But physics has been able to prove well, has been able to prove that basically, even no matter how accurately you do it, because of Heisenberg's uncertainty principle, there's no way for you to do exact measurements at all. Not about time, not about length, what else? Not about energy and not about momentum. And any of those four can be converted to the other quantities through one way or another, right? Okay, so that's a bit of TOK. So anyway, let's
Yeah.
continue.
Yeah.
All right. Plot the absolute uncertainty determined here in part D as an error bar on the graph, and then explain why the new hypothesis is supported. Let's go to the error graph first. Where would you? So you got 6. Remember, your uncertainty is 6, right? So from 40, how much can you go down and how much can you go up?
Wait. Sorry. 15% is percentage uncertainty, but
Yeah.
six is absolute uncertainty.
Okay. So basically, if we do this on the graph, I'll just do this on the graph here. Okay. So here, the whole graph is 15%, but only here do we have
Is 6.
6. Okay.
Okay.
All right. So how would you draw your 6 in this case?
We draw from 4 to
From
like the one above the line above
mm-hmm.
4. Like
Uh-huh.
not the second line from
Right.
40, but
Okay.
like right above the first.
Right. How
I wish I
much
could draw it.
would you
Sorry.
like how long would you draw those lines?
Oh, then I draw for 12 spaces.
The total
Starting
length is
from,
12, right?
yeah, total
Mm-hmm.
is from 12.
Mm-hmm.
But I'd start from like 30. Wait. 30. 30. Wait. 34.
34. Okay, 34. So you go here, something like that, and
And
then
yeah, 46.
somewhere here. Okay, done. 1 mark.
Maybe.
Great. All right, so let's zoom back out because you'll need the whole graph to answer the next bit. So why is the hypothesis now correct? Now, it says here in the question that it has how many marks? Let me double check. The question has only 1 mark, so you don't have to go into full detail here. But there's a lot of reasons why this now works. Okay. Okay. Remember, this is the reason why we try to linearize graphs in the first place is so that it's easier to analyze if everything matches or not, right?
Mm-hmm.
Now, how do we check if all these points actually follow the new hypothesis?
Mm-hmm.
The new hypothesis is
Oh,
f cubed is proportional to delta p, right? It's f cubed. How do you know
yeah.
if it is correct?
Because you can draw a straight line through all the error bars.
One, you missed one detail,
Uh,
but you're
from the
correct already.
origin.
Through the
From the
origin.
origin.
Yes, through the
Through
origin.
the
So
origin.
that would be the best answer here. Again, let's write that down here. The new
Draw a
hypothesis is
straight line through
supported because a straight line through origin, right? Through the origin and all error bars, and through the error and all the error bars, right, can be drawn, and that gives you your mark. Okay, here 1 mark. All right, great. So the last bit I think was easy. Okay, next question here. Student. Okay, we're now in part 2.
Mm.
Okay, we're now in part 2. Let me copy the questions first. No, just copy that. Okay, this one. We now have a student that conducts an experiment to determine the specific heat capacity of a metal cube. The cube is heated in a beaker of boiling water to a temperature of 100 degrees and then quickly transferred to an insulated vessel of negligible thermal capacity. Okay, the vessel contains water at 20 degrees and of known heat capacity. So state the other measurement that the student needs to make. So just one modification that the student can make to reduce the fractional uncertainty and for the change in temperature, and then discuss how transferring water from the beaker will affect the value of the calculated specific heat capacity. Okay, let's start with the first one. State one other measurement that the student needs to make. This in this case, I think it's going to be a good idea to check the data booklet because there's from the way this looks like, there's a formula that you need, right? Okay,
Okay.
all right.
Let's see.
Because look at the look at that. Can you remember the formula that would involve everything mentioned there?
T.
You have T,
Um,
temperature,
C. So
C,
MC delta
specific.
T.
So you need a formula with specific heat capacity C, right?
Mm-hmm.
So where would you look for this formula in the data booklet? Which
3.3.1.
topic? 3.1. Okay, I'll just copy that right away. I think you still remember it, but for the sake of argument that you don't, let's just put it here.
Okay.
All right. So these are the formulas from 3.1. So which one's going to be the more useful one right now?
The first one.
The first one. Okay. So what do you already have?
T.
You already have T, correct? I'll use blue again. You already have, well, I'm going to rewrite this to be sure, right? MC. So Q equals MC, then final minus initial, right?
Yeah.
Okay, there. So
So
uh,
initial is 20.
initial is given, right?
Yes. So it's 100 minus 20. No,
Mm-hmm.
you said initial minus final.
Okay,
No, final minus initial.
final minus initial. Do you have a final temperature there?
Oh, yes. 100 degrees.
No, that's your initial. You start with 100 degrees.
Oh, seriously?
Yeah.
Since he didn't.
Okay.
Okay.
All right. Okay. How do you understand the situation? Let's do this again before we continue. How do you understand the situation here?
The cube is heated in a beaker of boiling water.
Okay, so let's draw that. So there's your hot, right? And then there's your cube, 100 degrees, right? And
Mhm.
then what happens?
It melts
Mm-hmm.
because it's
It's
quickly
quickly
transferred into an
transferred.
insulated vessel.
So that means you have a second container, right?
Mm-hmm.
Because you have an insulated vessel, you have a second container. So this cube
Oh,
is then put in this container and
and
it's
it's a
put
lot
in here, right?
cooler.
Now, what
Mm.
else is in this container? Because the container itself has a negligible thermal capacity, we can ignore it, right? But what
Mm-hmm.
else is in this
So
water?
20 degrees water.
So this is water, but at a cold water, 20 degrees, right? Okay, let's write water here. Okay, so okay, so the question now is, given this, what do you need to know about? Well, there are a lot of possible answers here, I'll tell you that. Just by looking at the situation, there's a lot of possible answers here. It's not just one. Okay, let's go back. So you have your initial temperature, right?
Mhm.
And you know the heat capacity of one of those things, right? You either are looking for the heat capacity of the cube or you know the heat capacity of the water. In other words, it's already accounted for in the formula, right? So
Mhm.
what else? What do you not know yet? Delta Q,
T and
Q you need to calculate. So again, ignore
yeah,
this for
so
now,
we don't
right?
know
So we don't know M and you don't know.
C.
You do know
The,
C.
the cutouts.
It's here. It's known specific heat capacity for the water, and then you're looking for this for the Q, right? So C is known or looking for it. So there. In other words, we're not looking for something here that needs to be found. We're looking for something here that needs to be measured. Again, um, this is already known.
Oh, so measure the specific heat capacity of a metal cube.
Hmm. Well, you're gonna
That's the answer.
calculate that, right? The answer here is you
Oh,
don't know the mass yet. But remember, go
oh,
back here. You are trying to determine the specific heat capacity. So basically, everything else must be a controlled variable, right? You all
oh.
okay. I'll tell you in more detail on how exactly this experiment works. I don't think you've done this in school. I personally haven't. I've tried doing this in school, but students still have an issue with understanding how it really works. Okay, but the idea here is you know the temperature. You either know or will find out C, and then delta Q is a non-factor in this case. So you need to find out two more measurements. You need to find this out.
Mhm.
So the answer here could either be the mass or the final temperature. Okay? Both of these are the correct answer. One of these is enough. However, just like before, we can't leave it like this. We have to be specific, right? So what are we going to say? We can say mass of the block,
Um,
right?
the block, yeah.
Is there another thing that we can measure?
Metal cube.
Yeah, that's a metal cube. The block is the metal cube, right?
Yeah, that's true.
Hmm. How about,
Uh,
okay, in terms of the experiment, what's the bigger factor? The amount of hot water or the amount of cold water? In terms of the actual experiment.
in in this one,
Yeah,
amount of cold, no, hot water.
okay.
No, I say hot water because like if there's like more hot water than cold water, then the
Uh-huh.
hot water will stay hot
Well,
and cool
yep,
will heat up the cold water.
yep. And think about it this way. It's mentioned here in the text that the beaker is already has boiling water. So the water is constantly boiling. It's always 100 degrees, right?
Mm-hmm.
So when you put the block in there, you just make it reach 100 degrees every time. So in other words, you always start at 100 degrees, which is what the hot water is for. The hot water is not really a factor in terms of mass because you'll always get to 100 degrees. But you change the amount of cold water, you change your results in the end, right?
Mm-hmm.
So this could be the mass of cold water. Okay. Now, same thing, the final temperature, you could refer to the block. You could refer to the uh, final temp of cold water as well. Again, any one of these would work, but you see the pattern, you always have to identify something that should work here. Okay? So any one of these answers would gain 1 mark.
Final temp of cold water.
Hmm.
Massive cold water.
Hmm.
Yes.
Now,
I think massive block is the most obvious
yeah, the mass
one.
of the block would be the more obvious one. So this is actually the answer that I'm expecting most students to come up with in this case. Okay.
Mm-hmm.
All right. So let's go now to second question. Suggest one modification that the student can make to reduce the fractional uncertainty in the change in temperature of the metal cube.
Hmm.
Okay, let's go back. What is fractional uncertainty? We just discussed
The
this.
delta y over y equals
Okay,
delta a over a.
okay. All right. In this case, we want. Let's kind of think about this. Okay, so I'll do this here with red. No, orange. Okay, purple. All right. So in this case, think about it. You're looking for the fractional uncertainty in the change in temperature, right?
Mm-hmm.
So we want to say, instead of saying delta for change, I'm going to just, okay, I'm going to use delta for change in this case, okay? And I'm going to use D for uncertainty. Okay, just to make it a bit not confusing. If I use delta for both, it can get confusing, right? So what's going to be delta t equal to? That's going to be equal to initial minus final, as we said before, right? Sorry, the other way. Final minus initial. Okay.
Hmm.
Now we want the uncertainty in delta t, right? And since it's fractional, we're going to compare that to delta t, right? What's that equal to, as you said earlier?
Hmm.
Okay, as you said earlier, let's just go back here. We're going to use this, as you said, right?
Mhm.
Okay, but here's the thing. We don't know our delta y just yet, or our delta t just yet, or uncertainty in delta t just yet. We only know this. We know this thing. It's basically we start here. We start here, right? If you start here, which version of uncertainties do you work with?
Um, the mass,
Mm-hmm.
the the um,
All right.
no, the
All right.
mass and the temperature.
Well, okay, the mass and the temperature. Not quite. Okay, because remember.
No, the mass, the C.
Okay, hold on. I'm gonna just write that at the bottom. Just oops, so it's easier for us to refer to. I'll just write that thing. Okay. So remember that here. Um, let's start with this, right? And what will I have to write? Remember, the thing here is delta y is equal to delta A plus delta B. If, right? And I'm going to put that here. If y is equal to A plus or minus B. And then the other one is if y is equal to AB over C. I'll just do the whole thing as mentioned in the booklet. In this case, delta y over y equals delta A over A plus delta B over B plus delta C over C, right? Okay, so looking here, looking at our formula here, that the change in temperature equals Tf minus Ti. Which one, which pattern does it follow? Pattern 1 or pattern 2?
One, no.
Again, don't think of this delta as uncertainty. Think of that as the change. We're going to change the letter to D for uncertainty. Okay? Or in fact,
Wait,
let's
could
reverse
be.
that. Let's reverse that so it's easier even. So D would be change and delta is uncertainty. Okay? So if we do that, this is going to be dt here, right?
Mhm.
Mm-hmm.
So why can't it be one? Because it's plus or minus.
Okay. Well, yeah, it is. But remember,
Oh.
we're not looking for the value just yet.
Hmm.
Okay? Because the question here is not about finding the value. We're asked to reduce the fractional uncertainty. We have to do something about fractional uncertainty, right? So, what does this mean? What is the fractional uncertainty in dt? You do not have to overthink this. All you have to
Negative
do,
T I.
it's just going to be that over delta t. Okay?
Uh,
Basically, I'm just going to change our dt to this. So the
yeah.
uncertainty in Tf minus Ti, right? Over Tf minus Ti. Now, okay, so that's the way we do it if we just go all the way and just try to put some values in, right? But,
Mm.
okay,
Yes.
the, okay,
Yes.
the idea here now is how do you make this as small as possible? There are two things you can do to make this small, right? Oops, sorry, there's a
Really?
mistake here. There's no delta there.
Yeah. Okay.
Okay, just rewrite that. But there are two ways to make this as small as possible. What? Well, okay, CJ, I'll
Oh,
give you a clue. This is a fraction, right?
yeah.
Okay. How do you make a fraction small? Do you make the numerator bigger or smaller?
You make the numerator um
Small or big?
closer to the denominator.
Not necessary. I'll give you a clue. What's bigger, 1/2 or 1/10?
Okay, numerator. Make the numerator smaller,
Okay, make the numerator small and make the denominator
bigger.
big, right? So that's the idea here. So to minimize, okay, minimize what am I writing? Minimize the error by decreasing numerator, right? What's our numerator? The uncertainty in TF minus TI, right? Or increase the denominator. What's our denominator? TF minus TI, right? Okay, so what's going to be the easier one to do between the two? Do you decrease the uncertainty in the TF minus TI, or do you just increase the actual difference? Okay, let's put that in terms of numbers. Let's say, let's put this in terms of numbers. Let's say that TF is one. Oh, okay, that's how it's done. 100 degrees Celsius plus or minus 1 degree Celsius, right? And Ti is going to be, let's say, 30 degrees plus or minus 1 degree Celsius. Okay, how can we make this better? You either decrease the uncertainty or you increase the difference, right? So let's take a look here. Okay, I think you have something. What do you have?
Increase the ch- change.
Increase the change would be one way to do it. In other words, change this to what value?
Wait. 10.
10. All right, great. So that's one way to do it. It's only suggest, you don't have to explain, right? So you
Okay.
just say, um, decrease the, um, sorry,
The
not
change?
decrease,
No,
not
no.
decrease,
Increase the
increase the
change.
change in temperature, increase the difference in the initial and final temperatures, right?
Mm-hmm.
Okay, so if we
Hmm.
do that, that's already our answer. Increase the difference between um, initial and final temperatures. Okay, all right. I'm just gonna check the mark scheme here to see what it actually says. Uh, more smaller. Okay, and okay. Does it say? Okay, I don't think we get a mark here according to the marking scheme because we're not specific enough. How do you do it?
Oh, by placing it in a cooler container or
Okay, a
cooler
cooler.
heater.
So it starts with 20 degrees earlier. What do we, the water in the cold container. So what do we do with this new setup?
Um, decrease its temperature.
Okay, so
Decrease the temperature in the water in the container.
there we go. That scores 1 mark. So this means decrease temperature of water, of cold water, right?
Mm-hmm.
Okay. Okay. This is the best thing we can do, right? There are other possible answers. Okay. Um, excuse me. So what's the next possible answer here? The next
In decrease the final temperature?
Okay, yeah. Here, here
Or the
is we can't really decrease it because you're gonna decrease the difference if you do that. You have to increase the temperature as well.
oh,
But the problem is we're already at boiling of water. We can't really increase it, right?
mhm.
So we that 100 degrees is more or less set, right? However, let's focus on this bit, and I'm gonna change color to red so it's easier to see.
Is it the amount of water?
No, remember this delta F. This delta F can come from two things: either the thermometer, yeah, or
Sorry.
the all right. Okay, let me put that up. Either the thermometer or the what's this number of readings, right? Okay. Now, if it's a thermometer, you need a more precise thermometer here, right? If you have a more precise thermometer, your uncertainty decreases. Now, I'm going to have to say this really to emphasize this. You have to use the word precise here and not accurate, okay? Precise means you're getting smaller and smaller. You're capable of getting smaller and smaller readings, okay? Now, for the number of readings, what's the effect here? More readings means means uh, smaller uncertainty. Okay, and with both cases being this will both lead to a smaller percentage uncertainty. So more precise also leads to smaller uncertainty, which now leads to smaller percentage uncertainty. Okay.
Oh, so more readings. Okay, it's like a sample rate.
Uh huh.
So a higher sample rate.
Uh-huh.
Okay.
Now,
Oh,
in my opinion, this is an easy question to know once you know how to answer it, right?
yeah.
But it's not that easy if you just rely on the given information to you. But once you see what the pattern is, the answer is pretty easy. Just use a more precise instrument, or take more readings, or whatever needs to be made bigger later on. Okay. Now, we've already explained the reasoning, or yeah, we've reasoned everything out. Now we have a short answer. Our short answer is either increase the basically increase the numerator, decrease the numerator, or increase the denominator. The numerator is always uncertainty, so you use better reading techniques. And then for the denominator, that's the actual values, you look for bigger values. In other words, a bigger difference. Okay. All right. Let's put C on its own spot here before we move on. Okay. All right. The next question there is some of the water is accidentally transferred from the cube. So discuss.
To transfer it into the cube.
Mhm. So some of the water from the beaker, the hot beaker, okay, is accidentally transferred with the cube. So how will this affect the calculated specific heat capacity?
Well, it will definitely um, the value would definitely be wrong, increasing the percentage or increasing the uncertainty.
Mm-hmm.
Okay, so it'll increase the uncertainty, right?
No, we're not talking about the uncertainty here. We're talking about the actual value of C.
Oh, the value will either increase or decrease, right?
Okay, yeah, but which one? This is gonna be very specific.
Increase
It's gonna increase it. Why?
because it's hotter.
Um, okay. So you're basically saying read calculated value is larger than actual value, right? Okay.
Calculated value is yes,
Okay.
it's
Your
a lot
reasoning is what's your reason here?
because the water. Wait, is it the other way around? Because the water's hotter, that means the
Okay.
specific heat transfer has
Actually,
to be
okay,
lower.
I'll tell you this much. This is correct. Okay. Now give me a
Okay.
reason. Give me a reason why this is the answer.
Um, because the temperature of the water changed. Therefore, wait, the temperature of the water increased.
The cold water, you mean?
Wait,
right?
The cold water became warmer.
Mm-hmm. Okay. So cold water gets hotter, right? Gets
Yeah, therefore it needs more effort to raise the temperature.
gets hotter. So what effect does this have on the delta T?
Decrease.
Okay, delta T decreases. Exactly. This is 1 mark. Out of 2, you get 2 here. But
Wait.
remember, you have to, you don't, this by itself doesn't really, hold on, let me check the marking scheme just to be sure.
Uh,
Uh, yeah, I think that's gonna work. Eh, But I'm gonna have to say just add the second one to be safe, right? Okay.
increase temperature. Wait,
All
so
right.
the hotter something is, the more energy you need to raise the temperature.
And no, I wouldn't say it like this. Think this is the way think about this particular problem. So when you add the water in when you add the hot water into the cold water, so some of the cold water will go cool down the metal block, right? And some of the cold water will try to cool down the hot water. So not
Mm-hmm.
as much energy. So that basically means you're not using all of that cold water to cool down the block, the metal block, and because of that, you're using less energy to cool down the metal block for the same amount for some temperature change. But in fact, it seems like you're using as just as much energy to cool it down, but because some of it goes into the hot water.
Mm-hmm.
Okay, so okay, let me just check this. Okay, okay, I think just saying this is a 50-50, so kind of okay, I guess. Just saying the first part there of cold water gets hotter is a 50-50. Marking scheme here
See,
says additional energy is transferred, or the temperature in rise of water will be larger.
temperature
Or
of
the
water
temper,
will
yeah,
be
delta T
hotter.
decreases for block, right? Let's read it right there.
Mm.
Okay, all right. So, okay, so that I think that's the last question. Oh no, that's the last question on that section. There is, let's go to the astrophysics section here, option D. Okay, remember in option D, the questions basically repeat over and over again. It's just the situations are different, right? So once you know how to do a couple of questions in astrophysics, you should do well in the actual paper later on. Okay? Should is the keyword there. I'm not guaranteeing it, but I'm gonna give a 95% confidence level on that. All right, so here is the first astrophysics question.
Mm.
All right, hold on. What just happened? Oh, there we go. Okay, so here's the first astrophysics question. So you're given a nebula. The name is the ghost of Jupiter. So what's a nebula? So you see, we kind of go back to this. This wasn't a question before, but we still went through the idea, right?
Um, um, oh, nebula, nebula. Oh, we already did this one last time.
Oh, in class, I think,
Wait, really?
not with me.
Okay, no, because I remember I said that nebula is
Yes.
uh, a gas, a cloud. Wait, a dust cloud in space.
Yes. You know why this looks really familiar?
What?
This is the exact same question, but in a from a different paper. This is from the question we did last time that had this was a 2016 paper.
Oh, which one is this?
This is a 2021. No, 22. No, 22 or 23.
Were they lazy? Like they could have
No,
done anything else, like
no,
outline what is meant by a comment or
it's
something.
not. It's not laziness here. This is literally what happens. Um, in this case, because this is 2016 to 2023, right?
Mhm.
That's like a 5 year span, not counting the years that didn't have the paper three. So 2020 and 2021, there was no paper three, right?
So what paper is this? If this is 2021?
Sorry, this is 2022. My mistake. 2022.
Oh, okay.
Okay. So think about it this way: 2020, 2021, and 2016. That's like a 3 year gap in terms of the papers,
Mhm.
right? So this means they ran out of questions to ask. It could be a nebula, it could be a comet, it could be what else? It could be a star, it could be a red giant. It's asking these things over and over again. So in this particular case, we just got asked nebula twice.
Mhm.
All right. So once you memorize these definitions, you're set for this kind of question here. So for this, I'll just write, as you said, cloud of
Which definition do you think they will ask this year?
no idea. But it's definitely gonna be, I'm gonna guess, if I'm gonna guess, it's gonna be related to the stars. So it could be nebula again. It could be what a red giant is, what a main sequence star is, whatever those things are, what a supernova
Mhm.
is, and everything else in between. Yeah.
Okay.
Or it could be defining the two main units of distance. No, the three main units of distance. So these would either be stellar objects. So usually, yeah, or this could be astronomical distances.
Um,
I've never seen anything within the solar defining anything within the solar system like a comet, a meteor, a meteoroid, asteroid, satellite, dwarf planet. I've never seen those, but they could come up. All right. So
mhm.
let's just redo this. So again, this is a dust cloud in space. It's only one mark, so I guess one thing should be enough. Again, I'm just gonna check the actual mark scheme, see what it says.
I mean, it's probably going to be the same.
Yeah, I'm guessing it's gonna be the same, but I want to make sure. Am I looking at the right mark scheme? Okay, hold on. I want to see if I'm looking at the correct mark scheme. Oh, sorry, this is the 2023 paper, not 22. 2023. No, this. I think I. I think I may have closed that mark scheme I was looking at. Hold on, that's weird. 10, 11. The ghost of Jupiter. Outline what is meant by a nebula. Oh, I have the HL mark scheme open. Hold on. Is that the main issue? Yeah, I think that's the issue. I had the HL marking scheme open.
Oh,
Yeah. All right, let me open the 2023 SL mark scheme. Give me a moment. Let's see. Which one is it? Okay. Thirteen, 12. 11. No, it's not that one. I think it's this one. There. Okay. So, yeah, I got the mark scheme here now. Just for comparison. So yeah, looking at the mark scheme, it is in fact correct. We just say a dust cloud in space. Okay, that's done. So that's one mark. All right, so let's go to number 2. Astrophysicists have deduced the nature of this nebula from Earth. Outline how they can make these deductions.
Hmm.
Um, the nature of this nebula.
Um, by no, 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 no. What
Okay,
is the nature of this nebula?
I'll give
The
you a
ghost of
clue.
Jupiter.
I'll give you a
Oh,
clue. It
because
says nature. You always think of composition, right?
mm,
And then when you see composition, the thing you already think about is absorption and emission spectra. Yeah. So let's put this now into this context. So how would we answer this? Emission spectra. Okay. So in this
is it about
context,
emission?
mhm. So okay, if you want to use emission, how would you answer this? You can use both, just so we're clear.
Oh,
But if
which
but
one's easier for you or for
nebulas
students?
for me, if it's emission, it's easier to use emission for stars. But for nebulae, anything that doesn't emit light, it's gonna be easier if you use absorption.
Absorbs radiation.
Mm-hmm.
What
From
does it
where?
absorb?
From where?
From this, not this, the sun, right?
No,
Because it's at Jupiter.
not the sun. No, it's just called Jupiter, the ghost of Jupiter. It's not on Jupiter though.
Oh, what's it called? Something C. B something C.
Uh huh.
Um, microwave background microwave radiation.
Okay.
No. Okay.
I'm gonna give you a possible answer here. Okay, but again, the idea is always when you see the word nature of whatever, you think composition, and composition goes straight into absorption or emission spectra. Okay, so I would answer it like this. I don't know what this particular nebula is. So I'll just answer in terms of absorption, right? So, so if you want to draw light from behind the nebula, okay, passes through it, passes through, and what? The nebula then absorbs some of that light, and we observe this, and astrophysicists will observe the absorption spectra. Okay, the
What
nebula.
light does? Where does light come from?
Okay, basically it's like this. If this is the Earth, okay, this is our nebula, and we have of course, no matter where we look, there's gonna be stars, right?
Yes.
So all this light from the stars are gonna pass from the star to the Earth, but it's gonna pass through the nebula, right?
Mm-hmm.
Okay, so what happens is the nebula will absorb some wavelengths, will absorb some wavelengths, right?
From the stars.
Uh-huh, from the star's light, which okay, which will which astrophysicists observe, which is then observed, and the composition of the nebula can be deduced. Of nebula can be deduced. Okay, there.
Then the what will be deduced? The
The
what nebula?
the composition.
Composition. Okay.
Okay, there. The composition of the nebula can be deduced. Okay. So again, I'll say this again. When you see the word nature, the shortcut now is when you see the word nature, go to absorption and emission spectra. Okay.
Mm-hmm.
The logic behind it is when you see the word composition, nature, you think composition, then from composition, uh, absorption and emission. Okay. Let's go. Ready or let's ready to go to B, or you're still taking notes? All right.
Um, does composition only mean absorption and emission?
That's the only way we can be sure of the composition from our observations in space. Because we can't really go there and check what the actual compositions are, right? We cannot collect samples. So yes,
Right.
the short answer to your
Okay.
question is yes. It's only through
Oh,
absorption and emission.
because we can only look at it.
Yeah, we can't really
Is
go
this
there.
cosmology
Yeah,
or okay?
yeah. Because think about it. Even the closest thing we got samples from is the moon. We haven't even gotten samples from Mars.
Yeah. Okay.
All
That's
right.
fair. Yeah,
So,
I'm done.
all right, great. So let's go to B. So, which star appears to move more? It says deduce, so you have to give a reasoning behind it, right?
Mhm.
Okay. So, which one is gonna appear to move more? Star X or star Y? And why?
And why?
Mm-hmm.
Okay. So we use the equations. The
Don't
equation
you don't
is
even have to think about it like that. But
uh,
yes, you can use the equations.
is it the higher the parallax angle, the further it is?
Is
Um,
it the farther or the closer?
oh, the further it is, the less the angle,
Uh-huh.
because it'll be smaller.
Right. Okay.
Yeah.
So, yeah, that's correct. So let's use this thing. Okay. So star Y moves more, right? Because a parallax angle is
The
larger,
yeah.
right?
Mhm.
Since parallax angle is larger. Okay. I would expand. I think this already gets 2 marks like that. Yeah.
Mhm.
However, I'm gonna play this safe. I'm gonna say one more statement here. In this case, I'm gonna say this. You can use the data booklet to help you out with it, right? There's a formula in the data
Mhm.
booklet. Let's put in D1. So if okay, so
Oh,
what's
so
the
I just
form?
put the equation in.
You can, but you don't
Um,
have to. But you
so
can refer to it.
the first one. No.
Okay,
No, no,
the
no,
first one, right?
no,
So the larger
no.
the larger the parallax angle, the
The
smaller,
further it is.
the further it is, right? Or the larger the parallax angle,
Oh,
the smaller the
the
distance.
yeah.
Um, Refer to that. So if you wanna use this formula in your as reference to your answer, you can do so. That's just to keep it safe. But this is already 2 marks by itself, according to mark scheme. Okay.
Mhm.
All right. But I personally would play it safe and just refer to the formula booklet too when you answer. Next one, calculate in meters the distance to star X. Calculate the distance to star X in meters. This is this is easy, but what's this? Tedious.
Wait.
Okay. So again,
Okay.
calculate the distance to star X.
Okay. So use the first equation.
Mm-hmm.
52.3, 52.6 parsecs.
But remember, the answer should be in meters. Do we need the
Oh,
conversion
yeah.
factors? Yeah, we need the conversion factors, so I'll paste it here. Where is it here? Unit conversions.
Is it 9.46 times 10 to the 16?
Mm-hmm. But yeah,
Um,
I think your answer is correct in parallax or in parsecs.
4.98. Okay.
Okay, so there we go.
4.98 times 10 to the 18
Mm-hmm. Mm-hmm.
meters.
All right. So mark scheme, because this is a calculation. What's your answer again? 4 point?
Mm, 2 sig figs.
2 sig figs. No, not
Four,
quite.
okay. 4.98
No,
times 10 to 8. Huh?
no,
Really?
no. All right, let's do the solution here. Yeah, but again, your idea is right. You use this to find.
Oh, no, no, no. I did it wrong. I'm sorry.
Oh, what did you
I
do?
see my
Did you
mistake.
do star Y instead of star X?
No, I just did light years immediately.
Ah, okay. All right, all right. So you forgot to convert to light years first.
Yeah.
Okay.
Uh, I got 1.62 then times
Okay.
10 to the 19.
All right, correct. Yes. I'll just write it here again for reference later. So again, you do distance is equal to 1 over 0.019 for star x, and that's going to give you how many parsecs, right? So
Mhm.
0.19, and that's going to give you 526 parsecs, 0.32 parsec, right? And then you convert that to light years, and then you convert that to meters. So you multiply this by light year is 3.26 first, right?
Mm.
So times 3.26 times 3.26, that's 1715 light years, right? And then you change that with this 1 light year is this many meters, so multiply that by that number. Okay, so times 9.46 exponent 15 gives you final answer of 1.6 times 10 to the 3, 6, 9, 12, 15. Okay, there.
Mm.
18 meters. Done. Okay, great. Next bit on this question was determine the ratio of the luminosity of X to Y. Okay,
Mhm.
so put the question in there. What's the given information here? Let me double check.
I don't think there was a ratio. I think we have to find the luminosity.
No, there you are given some sort of ratio here. Hold on. You have to find the luminosity. Yes, true. You have to find the luminosity, but remember
Brightness.
you're given brightness, right? So I'll just post it here so we don't have to scroll up. So you're given these values. So find the luminosity ratio. Okay, I'll also post the data booklet formulas again.
Thank you.
Yeah,
Can I just put the luminosity equation on top of each other
yeah, you could do
and
that.
put in my calculator?
Mhm.
Okay.
In fact, I think that's the expected solution.
Oh, okay.
There we go. So,
The bottom one.
okay. Brightness and then luminosities. Yep.
Is it 4 pi d squared?
4 pi d squared, where d is the distance from the star to the Earth.
Mm-hmm.
Should I give you a clue here?
In meters or?
It doesn't really matter at the end, but technically it should be in meters. Technically,
Yeah.
okay.
Wait.
But because you're
Okay.
taking a ratio, it doesn't really matter what the distances are as long as they're in the same unit.
Mm-hmm. Okay.
X to Y, right? Okay.
I can't see the apparent brightness.
Oh, okay. Hold on.
Thank you.
There we go.
Is it 10 to the negative 9 or 3?
-9, correct. -9.
Okay.
I think you're doing better in these calculation questions in astrophysics than with the
I tend
conceptual
to do
ones.
better. Yeah, I tend to do better with paper 2 than paper 1 stuff.
Well, that's
So
true enough.
I am horrible with concepts. Yes. Um, hmm. It's gonna be a little bit
Mm-hmm.
for me to type this all out.
Right.
So the brightness doesn't determine how far it is.
No, it doesn't. In fact, it's the other way around. How far it is determines how bright the star is. There's another factor, the luminosity, right?
So luminosity
Luminosity will
helps
tell you,
determine how far it is
yeah. So it's those two things, the luminosity and the distance. Well,
and
think
the
about it
distance.
this way.
Sure.
It's easiest to think about it this way. Instead of thinking about stars, just think about a light bulb. The farther you are from the light bulb, the less bright it is, right?
That's true.
Same thing. If you have two light bulbs and they're equally distant from you, a brighter one would, well, a more luminous, a more powerful one is gonna be brighter, right?
Mhm.
So there's the idea there.
I got 5.41. It might be
Five.
wrong.
Okay. Uh, Let me check the mark
It
scheme.
looked like a nice number, so I hope it's right.
No, not quite. But you said 4 point
Yeah,
something, right?
I said 5.4.
5.4.
Still no.
No, but interesting. Your answer is interesting. I'll tell you the correct answer. 10.8. Your answer is exactly half of the expected answer.
No.
So why is it exactly
What?
half?
Wait, I did 8.4
Uh-huh.
times 10 to the negative 9
Uh-huh.
times 4 pi 1.62
Where'd you get the
times 10 to the
1.62?
19. 1.62 was
Okay.
the
It's this one,
x
right?
star x.
Yeah, star X. Okay. Correct. But okay, so your values are correct for star X. How about for star Y?
I got okay. I used the 3.1 times 10 to the negative 9 for the
Mm-hmm.
brightness
All right.
times 4 pi, and then times 8.12 times 10 to the 18, which was the I did 1 over
Okay.
0.038, and I got 26. 26 times 3.26
Mm-hmm.
times 9.6 times 10 to the 16.
Okay. Now I'm gonna show you a way to do it. The way I like doing it. I do the math first before the numbers. Right?
Mm-hmm.
Okay. But just so you know, what you did is acceptable and it's correct. It just so happens you got the wrong answer.
How did I get it wrong then?
Okay, so let's take a look, yeah? I think you got it wrong from the distance to star y.
Hmm.
Okay, the idea here, we have to look at both this and this to solve for the ratio, right? So because we're given the brightness, uh, we're just gonna do it like this: brightness of x over brightness in y should be equal to the luminosity of x over 4 pi dx
I did
squared,
that.
right? This is what you did, I hope, right?
Yeah.
Ly over 4
Oh,
pi
oh, oh, wait, wait,
dy
wait, wait.
squared,
No, I
right?
didn't do. No, I didn't do that.
What did you what did you forget?
I made L on one side.
L
I did
on
L equals
L equals
B
b
4 pi D
times
squared.
4 pi d squared b, right? So okay, if I do it like
B,
that,
wait, B, 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 B. Oh, yeah, 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 B.
right? Okay, so let's do it your way. Let's do it this way, right? So if we start from there, then I'm gonna do the x and y thing again. The x here, x here, x here.
I
Then you do the y here, ly,
realized my mistake.
right? 4 pi
I didn't.
dy squared by. So the 4 pi cancels out, right?
Mhm.
So what are we left with? But here's the thing. Because of this, I can just say d is equal to 1 over p.
Mr.
Yeah,
Dennis, I
right?
messed up. I didn't square it.
Ah, I see. That's where it happened. The squared. And that so happens to make your answer half of the correct answer,
Yeah,
right? So from here, we have to square that, right? Now, did you
yeah,
actually solve for the d for each of these? I think you did, right?
yeah. In
But
meters.
in my case, I will not. I'm just gonna actually just write that here as bx over px squared all over by over py squared. That's it. So all I'm gonna do now is put my values in. This is equal to um what's my bx? 8.4. Let's just see. They're both 10 to they're both 10 to the minus 9. So I that 10 to the minus 9 will cancel out on the stuff. So I'm just gonna write 8.4 here right away, right? Over 0.019 squared divided by um 3.1 divided by 0.0. Okay, I have an extra 0.038 squared. Do the math and done. Yeah. So if it's only the squared you forgot, then that means you do know what you're doing. You just have to be careful. Okay. All right. Uh, wow, time flies. We're now on the last question for option D. You mind taking a quick break for now, like maybe 3 minute break, then we continue.
Sure. Oh, I also wanted to ask one more thing.
Yep.
Do I? Is it okay if I always keep my answers in either parsecs or light years? Because unless it asks me to convert it to meters.
In here, yes. Whatever the more
Well, in
convenient
like
unit is.
most
Yeah.
cases.
In most cases, either way should be yeah, meters, light years, parsecs should be fine. The only exception
Mhm.
is like the earlier question where you had to convert everything to meters. Yeah.
So keep in parsecs unless asked to change.
Yes.
Thank you.
All right. Okay, so let's take a 3 minute break and we'll continue from there. Okay.
Okay.
All right. Okay, and me on the stream, yes, I have to say it as well on the stream. I am going to take a quick break. Oh, is this astronomy? Sorry, I just found the messages on the stream. Yes, this is astronomy. Um, yeah. If this is about the luminosity bit, light takes years. It's not about the time. It's about the distance. It's more like it's more spread out. Okay, so because it's more spread out, since the area is bigger, but there's the same amount of energy, so there's less energy per unit area, and less energy per unit area, or less power per unit area, then that means you're uh for that particular bit of area you don't get as much light. It's dimmer. Okay, so that's the reason behind it. Right. Again, we'll take a quick break. Uh, I said 3 minutes for TJ. I'll be back on the stream in a minute. I'll just take a quick break. All right. Be right back. Back. All right, I'm back, and I'm also gonna go back here on stream on the lesson. Okay. All right. Hi, CJ. I'm back.
Mr. Dennis.
Yep.
I also wanted to ask.
Go ahead.
What's do you know SPH
SPH. The school, you mean?
school?
Yeah. The school here, you mean, right? Yeah, I'm aware of it.
I was watching them play yesterday.
Oh, I see.
Football.
Football. Also, they stream their matches. Okay.
I was no, they were playing it at in Thailand.
Oh, they're in Thailand. I see. Okay.
Yeah. Mm. What was your school again?
SPH is Pelita Harapan. Sekolah Pelita Harapan, which is, yeah,
Okay.
Pelita Harapan. Then school is
Really?
Sekolah. Here came from Dutch.
Okay. Oh, okay. Is your school close to it?
Not really that close, but I know where it is. Even though
Okay.
Jakarta's quite big, it's easy to go places here,
Oh, wait.
despite
What
the
was your
traffic.
school again?
My school.
Yeah.
Okay. Wait. Should I say what my school is? Well,
Why not?
I wouldn't say it out loud now. Not on the stream, at least. I'll tell you
Okay.
later. Not
In
on the
the
stream.
in the
I'll
chat. In the
I'll
chat.
tell you in the chat. So I'll not say
Okay.
it on stream. There. All right. Give me a moment. I'll put it on chat.
Thank you.
Now, why do you ask?
Because I have a friend that goes to schools in Indonesia.
I see. All right.
Mm.
Okay, I sent it to you. So go ahead, just
And
check it out.
okay. Yeah. Okay. So my friend said that school is a vegan school.
It is.
What does that mean?
Well, it's not really vegan. It's vegetarian.
Oh, okay.
Okay, for those in the stream, if you don't know what I'm talking about, there are many schools here in Jakarta. I think there are 2 or 3 schools here in Jakarta that are vegetarian. So that should narrow down your choices.
Oh.
uh, but yeah, it's not the only one, so they can keep guessing.
Mhm. Is everyone? Oh wait, is the ethnicity of everyone there like just one group? Like, like what I like? Is everyone there? I sent it in the chat.
Mm-hmm.
Okay, that's similar to my old school as well.
Yeah. Yes. Short answer is yes.
Okay, thank you.
Of course there are others, but mostly them.
Mhm.
Yes.
Okay, thank you.
All right.
Yeah.
But the other school is mostly the other group. I'll send it
The
in chat
other
as
group?
well. I'll send it in
Okay,
chat as well.
okay, thank you. Oh, yeah, I was thinking. Yeah, okay.
Yeah, but yeah, so I think like two of the schools are from the group you said, and the other school is from the group I said.
Mm,
Okay,
so there's not many.
not that many.
Okay.
So like I said, if you know where I teach, if people know where I teach, it's an easy deduction on which one it is.
Yeah, okay, I'm sorry.
No, no worries. That's why I didn't want to say it in the chat box. Okay, or
Because
rather
it's
in the
easier to
stream.
narrow down.
Yeah. All right. So
Oops.
anyway, no worries about it. You could ask and I can answer, just not on the stream.
Okay.
All right. So let's continue. Where were we? Aha. I think this is where we are. Okay. This question, you've seen this question so many times before.
Outline what is meant by a nebula.
No, not that one. This one is about stars now. You have seen this question so many times. Asked
Oh
in
no.
different versions. There are you have the
Oh,
Hertzsprung-Russell diagram.
main sequence star.
Hmm. You have the
Mm-hmm.
Hertzsprung-Russell diagram and okay, identifying which one's main sequence, giant, neutron stars, black holes, and white dwarfs, right?
Oh, yeah.
State the element that is undergoing nuclear fusion in star C.
Let me write this down real quick.
Hmm.
Um, wait. So there's, I think you said this before. You said like hydrogen, helium,
No,
and something else.
no,
Huh?
one of those is correct.
Oh, helium.
Not quite. It's hydrogen. Where's star C? Look at the diagram. Where is star
Darcy's
C?
main sequence.
Main sequence. And main sequence will always burn hydrogen.
Yeah.
So the answer here in A is hydrogen.
Hydrogen.
Hmm. So let's note that here again. So this is hydrogen. Okay. Why? Because here, this is hydrogen to helium, right?
Mm-hmm.
Here, these are your giants. Okay. This is main sequence, right?
Mm-hmm.
This is giants. And this is always helium to others, right? And this would be
Yeah.
white dwarfs.
So it doesn't go through any.
Okay. Yep, no, and this is no fusion. Okay. Where
What's
would
the temperature of that then? Of white dwarfs?
uh white dwarves would be
Just one or three? I mean,
okay, hold on.
3K maybe. I
They're
don't.
they're
No.
still pretty hot, but they're
Yeah.
tiny.
Why?
They're basically they're really hot because of the fact that once they stop their fusion, once the fusion stops, the remember that the white dwarf is not the whole star. The white dwarf was the core. And the core is typically hotter than the surface of the sun, the star, right?
Hmm.
So no fusion. Okay. Again, think of this as core remnant, right? So again, the idea is cores are always hotter than the rest of the star. That's
Hmm.
why white dwarfs stay hot because they were hot to start with. Okay.
Yeah. So they don't get cooler, or they take a long
They
time to
take a
cool.
long time to cool. Well, in terms of the human lifespan, it's going to be a long time. Okay. But
Okay.
in terms of what's this? The lifespan of a star or the age of the universe for that matter, uh white dwarfs are pretty fast lived.
So they have short life.
They have relatively short lifespans. Like if I'm not mistaken, the longest one would take around a few 100 million years. That's the longest one. A few 100 million years.
Still a long time.
So again, relative to us, that's still long. But compare it to like how long a star stays in the main sequence,
Hmm.
it's up to billions of years. Maybe even 10 billion, right? In the main sequence. So white dwarfs are relatively short lived.
What about the sun?
The sun
What do
right
you
now
think?
is a middle-aged main sequence.
Middle age. Oh,
Middle
so
age.
we still have more billions. Wait, so you have another 13 billion years to go?
Another 4 billion to go. 4 to 5 billion.
Oh no, that's not long left. No,
Again,
what's
human
gonna happen?
lifespan, that's still quite long.
Yeah, but I feel bad for the people that are like.
Well, well, you in all honesty, since you mentioned that, before we continue, okay, since you mentioned that, I've had that particular, I wouldn't say worry, but that particular worm in my head since I found out that that's gonna happen. And when did I find out? I was still a kid, like I don't know, less. I was younger than 10 years old by that time when I found out about this.
Hmm.
And then I thought, okay, the universe itself is only around 14 billion years old, and then our sun is in the middle of its life. So what's gonna happen eventually? So yeah,
Yeah.
same thought process. And then that's kind of sad, isn't it?
Yeah, that is pretty sad.
All right. Oh well. Let's go to the next question here. So
Wait, do we ever have to worry about it, or will we be in Mars by then?
by then, okay, here's the reality of the situation. Because we tout ourselves as being the smartest species ever to live on this planet, right?
Mhm.
Okay, so that means one of two things. Either we're smart enough to figure it out soon that we'll leave the planet before that happens, or we're gonna be smart enough the to destroy everything on Earth, including most people, by the time that
Before it
happens.
happens.
Yeah,
I think it'll be the latter.
I the sad reality is I think it's the latter too, but the optimist in me says it's the first one.
Yeah, that's
All right.
understandable.
Okay. So anyway, let's get out of the sad situation and go here.
Wait. I'm sorry. What do giants like? What fission
They
fusion do they go through?
they undergo this is basically helium to others. I say others because
Mhm.
helium, the way helium is fused in a giant, it can produce carbon, oxygen, or yeah, it's either oxygen or nitrogen. No, not nitrogen. Carbon. It's either carbon or oxygen. And then afterwards,
Okay.
those other things will fuse further into form other stuff like the metals,
Okay.
like transition metals.
Do
Let's
I need to
say
remember those?
no, no. All you need to remember here is it's hydrogen to helium, then helium fuses in giants.
Okay. What other giants are there? There's red giants. No one else.
Generally speaking, nothing else. There are a few out there, but in terms of the syllabus, they're all red giants.
Okay.
Okay.
So white dwarfs are just core remnants. Okay. Thank you.
All right. Okay, let's move on. Okay, so let's take a look at the second question. Explain why star B has a greater surface area than star A. Okay, I'll keep the diagram here. So star B and star A. Why does B have a larger surface area?
Where's oh, because it's a giant.
That's not a good enough of an answer.
Oh, because it's hotter and more luminous. That must mean it's burning more things.
What's hotter, A or B?
B. No.
It's not
B, yeah.
hotter. It's
No,
colder.
wait, what?
B is
Wait,
colder.
yeah. Okay, but B is more luminous. No, it's not. It's
approximately the same, right? Okay, I'll give you a clue here. You're on the right track. Use the formula booklet.
Wait, it has the greatest surface area because it's a formula booklet. Wait, sorry. Let me format this.
All right, again, I'll put the whole thing here for reference. Right there. Pasting. Okay, I'll put this here for reference. There. Remember, you're comparing temperature to luminosity. So that's what we have on the graph on the HR diagram, right?
Mm-hmm.
So we have luminosity and temperature. So which formula is the one best used here? But yes, you're right.
Oh, second D1. D1, second one.
It's this one, right? So, same luminosity, as you said, luminosity, but
Same temperature as well.
they're not the same temperature.
Oh, no, same temperature. Same. What else is the
Luminosity is
same?
the same, but which one's different? The temperature. B is colder, right?
B is colder, yeah.
B is colder. Okay. So from there, so from here, so this means uh this means that
Can I make a ratio?
yeah, you can.
Mhm.
So that means that area must be larger of B must be larger, right?
Mhm.
Okay. Larger due to um, T to the 4 is proportional to 1 over area, right?
Mhm.
That's what it means. Everything else is the same. So the bigger the area, there, for the same luminosity, okay? That's the answer. Okay. What is that it? No, there's still another bit. Two more questions on astrophysics. Okay, after this, you want to do paper 2 or paper 1 after this?
1.
1. All right.
Wait. So I don't have to put an equation. I just. Wait, can you move up real quick?
You don't have to. You just have to just reason it out in this case. This is the thing I like about paper 3. You don't really have to go all the way to the formulas. You just have to be able to reason them out. Okay.
Okay.
All right. So C, we have to go back to the HR diagram. And then for D, outline where the radius of a neutron star reaches a stable value. Oh, this, you have to know this, I think. So
Wait,
D.
can you scroll back up?
Yes, I will do that for the HR diagram. Hold on.
Explain why. Because wait. Oh, you said Same luminosity, but B is colder. This means that area of
Mm-hmm.
P. Okay, thank you.
Mm-hmm. All right. How about this? How about C?
Um, a line to show the plus.
Okay.
Okay. Um, I think
S-
it's just I'm just gonna draw a straight line
mm-hmm. Why straight line?
because I mean I'm looking at the main sequence and
Mm-hmm.
it doesn't seem to like have a principal axis. It just still
Mm-hmm.
goes down as well.
Right. Okay. So basically you're gonna say that for C, you're gonna use this. It's something like this.
Mhm.
O- Okay. I think that's right. Um, okay. What Okay. So do you have you can do as long as you do some sort of line like this gives you your mark according to the mark scheme. Okay.
Yeah.
All right. Reasoning is this. You're right. Since they're all of the same volume, that means they should have the same surface area.
Oh, aren't they perpendicular to something?
No,
I don't
not
know.
necessary. Not necessary. Um,
Okay.
okay, let's just reason it out here again. Again, because the idea here is that same volume means same area, right? In other words, they're basically gonna be identical white dwarfs,
Mhm.
right? And since they are identical white dwarfs, the only thing that would change now is so they're still gonna follow that luminosity thing. The luminosity here will be proportional to T to the 4, right?
Mhm.
So basically you're gonna get something like this. This case, this is already a logarithmic graph on the y-axis. So your logarithmic graph on your y-axis means this is going to be a straight line. Okay, straight line. Okay, so I'll just say it, the reasoning here. Okay, straight line in HR diagram. Yeah. Okay.
Mhm.
So
Wait, did you write T4 is proportional to 1 over A?
earlier, yes, it's this one. Yes, but
Okay.
now we're doing
So
this. We're doing. I think I better highlight that. Hold on. Highlight. I'm doing this one now.
how do you know it's proportional?
Um, same. It's the same thing with this.
How do you
It's
know the one before was proportional?
mhm. In this case, the one before, the one that's the same for both for the two stars before is the luminosity, right? But here in
Mhm.
C, the thing that's the same would be the area. So the luminosity. So again, because the formula is actually, let's write it here. The I'll just write it bigger. Sigma is that no E A T to the 4, right? Because again, because of this part here, same area, meaning the area doesn't matter, and that's also a constant because the area is a constant, right? So this means that L is proportional to T to the 4, and that's what we have there. Okay. Okay. Um. All right. And then where did I get that idea that it's a straight line in the Hertzsprung-Russell diagram? Here you will see that this doubles, the temperature doubles for each unit you go to the left, right? And then
Mhm.
and then look at the luminosity. The luminosity for each what's this for each tick, it goes up by 10 squared by 100. So in other words, this is a logarithmic on logarithmic graph. And logarithm on logarithmic graph will always give you a straight line if you have powers. Okay. That's Okay, but that's the main idea for C. All right. How about you have any? Is that clear? Before we go on to D, is that clear?
I don't think I remember logarithmic of
Yeah,
logarithmic
you don't
moving
have to.
straight.
You don't have to remember that. All you have to know at this point is that this, the thing here, is gonna be a straight line in the Hertzsprung-Russell diagram. Okay.
Yeah.
All
Okay.
right. That's all you have to remember. But you don't even have to remember that all the way. All right. So let's go to D. Last one. What's your answer there? Some stars on the Hertzsprung-Russell diagram are likely to evolve into neutron stars. Outline why the radius of a neutron star reaches a stable value. Okay, if you don't know how to answer it, we can go back
Oh,
to
I think I
something
got
else.
it. I got it.
Okay, go ahead.
Something about. Oh no, I'm thinking about thermal. Never mind.
Okay, I'll give you a clue. All right, this is true for anything. This is true for a star. This is true for a planet. Okay, but basically let's just draw the star here, right? If that's your star and this is a stable size, right? So
Mhm.
if this is a stable size, then that means, remember that the star is getting pulled in by gravity, right? So that's gravity, right? What is stopping it from collapsing? There must be a force going
Atmosphere.
outwards, right? It's not necessarily the atmosphere. Let's just call that outward force, right? Or outward
Mhm.
pressure. This again is true for everything in the universe that's spherical in size, up to a star. Okay, so this includes black holes. Well, not black holes. This includes neutron stars, white dwarfs, red giants, main sequence stars, planets, anything spherical. Okay, true for anything spherical. In fact, it's true for a basketball or a football, right? What's causing it to collapse on itself? It's basically the material trying to pull itself together, right? What's pushing it
Mhm.
outward? The air pressure inside, right?
Mhm.
Okay. But anyway, since this is true for any sphere, remember a neutron star is also a sphere, more or less, right? So, in other words, this is your answer. The only problem now is this outward pressure is different for each type of star.
Mhm.
Okay.
So a neutron star is a star that has equal outward and inward
Mm-hmm.
pressure. By
Yeah.
inward is gravity.
Yeah. Inward is always gravity, correct. But again, the outward pressure is different for each type of star. Okay. Uh,
Mhm.
okay. Now, what's the outward force? I'll just draw that on a table. Okay. So if this
Is
is the
it?
star and this is the outward force, okay. If the star is main sequence or giant, okay, this is properly called radiation pressure. Okay. This is the proper name. Okay. But for your the easier way to think about this, and I'll put this in bracket, and this is the more important one for you. This is the pressure generated by all that heat from fusion. Pressure from fusion. Okay.
Mhm.
Okay. Now the next type are the white dwarfs. Okay. The white dwarfs. Okay. Dwarfs. Okay. They're the outward force is electron degeneracy.
Yeah. What is degeneracy?
Okay. Okay, I'll explain this first in the more technical way and then I'll simplify the language, okay?
Is
Um
there neutron degeneracy?
yes, neutron degeneracy would be for neutron stars.
Mhm.
Okay? Neutron stars would be neutron degeneracy. Okay. Now the idea here is it's more quantum mechanics that's at play here rather than classical mechanics. Okay. But in terms of, let's just say it in classical mechanics first, it's easier to imagine. These in certain cases, the electrons, let's start with the electrons. When they get close enough to each other, they will repel each other more or less because of their charges, right? But when
Mhm.
gravity starts winning, they're still gonna get pulled in together, right? And basically the electrons are gonna touch each other, so to speak. But when that happens, quantum mechanics is gonna say that once they start getting close enough to touch each other, so to speak, the equations that dictate how electrons move around say that they cannot become okay, let's think about it this way. So remember that electrons can be thought of as waves, right?
Mhm.
Okay. Now, the waves, each electron has a particular wave, and the information carried by that what is that one of the things about electrons is they follow what's called Pauli's exclusion principle. Okay. This is, you
Mhm.
don't need to know about this exactly, but Pauli's exclusion principle says that for any subatomic particle, for any subatomic particle, the what's this? Okay, for any
Mhm.
subatomic particle, uh they cannot exist in the uh exact same quantum states, because if they did, they'd turn into one particle.
Oh! Like if they're turning in the same direction, they would be this and overlap each other. They'd be the same. That's
Okay.
why they have to be like turning different directions.
Well, the word is not turn, but yes, the word is actually spin, because it's
Spin.
not it's
Sorry.
not yeah, it's fine because that's what you would think of when you say, when you hear the word spin, right? But that's the idea. If you're familiar with chemistry, that's why
No.
we oh, you're not familiar with it. That's why in chemistry, you can only have two possible electrons in an orbital, right? So for
Mhm.
example, helium will always have two electrons. The moment you introduce a third electron, it cannot stay on the same shell. It goes to the next shell, right?
Mhm.
Okay. It's the same idea with white dwarfs. When you have all these electrons, all those electrons have to occupy different states, different spins, different locations, different speeds, different everything except charge and mass. Okay? Because once two electrons have the same position, the same spin, and what's the other one? Whatever, everything being the same, they cease to exist as two separate electrons and they become one electron.
Do they superimpose or do they just like
In terms of quantum mechanics, correct. They do superimpose, and the superposition of the two electrons doesn't result to a heavier electron. It results in one electron.
okay? So
Okay.
it just deletes. It's like okay, I know what you mean.
It's
Hmm.
like yeah, the word delete
It's like having
is
a doppelganger, and
yes,
then
it's
you
like
guys just
having a
walk into each other,
yeah. And then when
and
you're
then just
doppelganger and you get together, the doppelganger disappears, right? You become
does
one
it
person.
disappear, or does it
No,
like
you merge into one.
transfer anything?
You just merge into one. Okay. The
But
energy
nothing
that
changes.
nothing changes. Probably some energy is released, but aside from that, nothing else. Hold on. Yes. You said hello already earlier. Ah, say hello again then.
Hello.
All right. Okay. Ah, we're almost done, huh? Yes. Okay. Okay, miss you too. All right. So, anyway, same idea for neutron degeneracy. The idea here is electron degeneracy for white dwarfs prevents the gravity from winning. There's just the
Mm.
gravity isn't strong enough to oppose the electron degeneracy. But once you hit neutron star masses, the gravity's strong enough to overcome electron degeneracy. So all those electrons start merging with stuff. What do they merge with? They merge with the protons. That's why neutron stars are made of neutrons, basically because the electrons get pushed into the protons. Okay. Now,
Mhm.
the neutron star itself, once it's in the neutron star phase, what's keeping it from collapsing further is neutron degeneracy. Okay.
Mhm.
And once we have neutron degeneracy, it's the same idea. The neutrons can occupy different states. Some of those states can be the same as long as it's not all the same, right? Now, in a black
Yeah.
in a black hole, what happens is the mass is still too much for even neutron degeneracy to prevent it from collapsing. So the idea in black holes is that it's literally, well, not literally, at least in the idea, it's basically a hole. Now, the mass is so small that mathematically it's gonna have a zero size, mathematically at least, because nothing's gonna prevent it from collapsing onto itself, right?
Mhm.
So the black hole itself has no size, but it's got so much mass, right? That what happens basically is yeah, it kind of makes a hole in space. That's why it's
So
called a
only
black.
small masses
Yeah, they're
make
not
black holes.
they're not small in terms of the mass. Their mass is big,
I
incredible,
mean
right?
size.
Small in dimensions. Okay,
Oh, so they're dense.
they're incredibly dense. Black holes are neutron stars are already dense. Black holes are even more so.
So they collapse on each other.
Mhm. So black holes have so much mass that once they overcome neutron degeneracy, nothing is going to prevent them from collapsing further. So
Mhm.
imagine something the size of the solar system in the size
Mhm.
that's the size of an electron. That's how tiny the actual, maybe even smaller, but basically that's how tiny the black hole actually is. But since we cannot,
So this is
go ahead,
sorry.
go ahead.
This is electron degeneracy.
No, that's black holes already.
Oh,
Okay. So
okay.
electron degeneracy is again, you compress the material so much that the electrons start pushing back due to electron degeneracy. Neutron stars are gonna be compressed until the neutrons are the ones doing neutron degeneracy. Black holes exist because not even neutron degeneracy can stop the gravity.
Okay. So what
Right.
exactly is degeneracy?
Okay, the word
Mhm.
degeneracy here has a specific meaning in quantum mechanics. It just means that, yeah, it goes back to what we talked about. So when we say degeneracy, it means that no two particles can exist in the exact same state.
Okay.
That's it.
Mhm. And
Okay,
in neutron stars, it's just neutrons that
do the
can't
degeneracy.
exist in the same state.
Yeah,
Oh, the neutrons that do the
yeah.
degeneracy.
So it's the same thing. So again, white dwarfs, the electrons are doing the degeneracy. The electrons cannot exist in the same state, right? Neutron stars, it's the neutrons that are undergoing degeneracy. So no two neutrons will have the same state. Okay.
Mhm.
All right. So going back to answering the question before we end this particular bit. Okay. Outline why the radius of a neutron star reaches a stable value. Again, the idea is this. So how would we say it now?
Um. Oh wow, we went on a tangent. Um.
Actually, we
Wait.
didn't because
Uh.
our answer's right here.
Because outward and outward pressure is outward force is equal to gravity.
But
Therefore,
you have
it is
to
stable.
yeah, but remember the question specifically says neutron star. So
The
you have to say
radius.
what the
Oh.
outward pressure is.
Mhm. So the neutron stars. What is the outward pressure? Oh, radiation pressure.
No,
Huh.
radiation is for giants and main sequence.
I can't say outward force.
You cannot say outward force because you have to be specific on what the outward force is.
Oh, neutron degeneracy.
Yes.
Okay,
Okay.
okay, okay.
So the answer.
So,
So going back to this.
so the radius of a neutron star reaches a stable value
Mm-hmm.
because the the neutron degeneracy equals gravity. Or can I just say neutron degeneracy equals gravity? Equals gravity. Therefore, um, neutron star doesn't collapse.
Mm-hmm. Neutron star does not collapse. I'm gonna give this is 2 marks, right?
Yay.
I'm gonna give you two
Oh, I got
marks.
one. Yes.
Okay. Earlier, when you just said that gravity is balanced by outward pressure, I think that's gonna
Mm,
get 1 mark.
okay.
Okay, let me check mark scheme to be sure. Hey, you know what marking scheme? If you're applying it leniently, you could get 2 marks for saying just outward pressure or outward force.
How does that work?
You just the way you said it earlier. So the gravity is balanced by an outward force.
Hmm.
Yeah, it's only 1 mark because the main word we need here is degeneracy. Yeah,
Hmm.
neutron degeneracy. So yeah, the second version is 2 marks.
Better one.
This is 2 marks. Okay, so just saying outward pressure equals gravity is 1 mark. Okay,
Hmm.
all right, good. All right, so we're done with paper 3. Oh gosh, it's like it's less than a week. No, it's about 2 weeks from now, isn't it? Less than 2 weeks.
Yeah,
Yeah. Huh. All right, let me just
it's
see.
over. It's over for me.
Oh, apparently it's not done yet. We have another question. We have one more question.
No. Okay.
Okay, let me just make sure that it is the last one. Yeah, this is the last one. For paper 3. Galaxy D. Okay, you've seen this question, no, a similar question from before. I don't think they actually changed the question. They just changed the conditions here,
The year.
the
Oh,
specifics. But the actual question I think is the same. Okay. Okay. There we go. So we have a galaxy with a redshift given. Let me put in the relevant formulas again.
do you know what topics they're adding in the new syllabus?
I do, but I have actually forgotten since I don't teach it this year. I'll be teaching it next year, hopefully.
Hmm. Do you think they remove astrophysics?
They didn't. They integrated it into because the idea here is they actually integrated all the options now into the main syllabus.
Hmm.
So no, astrophysics as a topic is gone, but astrophysics itself is now part of.
Topic 7.
Yeah, somewhat like that.
Hmm. Okay.
All right, so let's take a look here. So calculate in megaparsecs the distance of galaxy D using a Hubble constant of that. Oops. Okay. You know what? I'll repost the relevant formulas here.
Thank you.
I think it's a bit too small. Oh, you know what? No, I don't have to do that. Hey,
What happened?
what happened?
Hmm.
Hold on, let me check what happened. Oh, okay, I made a new window. All right, there we go. Let's delete that. I'll just zoom in. There. I think you can read that. Okay. There. All right. So redshift is 0.13, and therefore find the distance given that Hubble constant of 73. Which formulas do you need?
1 sec. Okay. Um. Wait, I can't see the. Wait. I'll
Okay.
just open the equation.
All right, there. I'll zoom in a bit. There.
The left side is cropped. It's okay. I'll look at the equations, but I need the question.
Oh, there we go.
Distance and negative. I mean, Hubble. D3,
Uh-huh.
third equation. No, third equation, yes.
Third equation, yes, you'll need that.
Mm-hmm.
But thing is, you don't know the speed, right?
I don't.
How do you find the speed? You're given the redshift.
Oh, there we go. V over C.
Okay, you'll need this. Okay, correct. So solve.
Okay. So V over C equals no. 3 times 10 to the 8 times 0.13.
Okay, correct. So V, let's just put that here. V equals 0.13C. Then
Which equals
calculate.
3.9 times 10 to the 7.
Okay. All right. Equals 3.9 times 10 to the 7. This is, remember, in meters per second, right?
Okay.
Mm-hmm.
Oh, and then we can use that equation now. So that divided by
So then use D
73.
equals
73,000.
73,000, correct. Over, actually, no, not that, right? Something's missing. It's going to be 3.9 here, right? 3.9 times 10 to the 7 over 73,000.
Over 1,000.
Okay. So
I
what's
got
that?
534. 584 for meters per second.
No.
Meters per second.
No, this is a distance, so this should be
Oh,
meters, right?
megapars. Oh, meters. Yes.
Okay, but it says here you have to do it in megaparsecs.
Okay, times 3.26. No. Yes. Is it just times 3.26?
Okay, I'm gonna give you a clue. This is already actually in megaparsecs. Right.
Times 10
Okay.
to the
Why?
negative
Why is this already
6.
megaparsecs? Just so we're clear, because I think a lot of students will get confused here, right? So I'm just gonna have to say that this speed here is already meters per second, right? And then you remember you said that was correct. That was 73, and then you have 1,000. This is now meters per second, right? Per megaparsec. So you see the meters per second cancels out already. You're left with megaparsec. So that's correct. The answer is 534 megaparsecs, right? However, again, to be safe, you round that off to the correct number of sig figs. This should be 530 megaparsec to 2 sig fig, okay? Okay. Okay. All right, let's go
Wait.
to B. Oh,
Is the Hubble constant already written in megaparsecs?
yes,
Like
it's right
usually,
here. It's
always.
yes. The only thing you need to convert here is the kilometers per second to meters per second. That's the only thing you need
Mm-hmm.
to be careful about. But it's always in megaparsecs already. Okay. What else about the Hubble constant? The Hubble constant can change depending on the problem. Okay. Some
Mm-hmm.
some problems will use 73, some problems will use 72, some problems will use 70. I think the
But
last
I
prop
still just convert it to meters.
just convert it to meters. Doesn't matter
Mm-hmm.
what the value is. Okay.
Mm-hmm.
All right, let's go to the next one. Hubble constant gives an age of 13.4 times 10 to the 9 years when assuming a constant rate of expansion has occurred. Okay, determine in years the age of the universe when the light detected on Earth now was originally emitted from the. So which form? So we're done with this. We're done with this formula. And we're done with this formula. So which
Mm-hmm.
one? Which one is left?
The last one.
The.
No.
Mhm.
The last one is the age of the Earth. Or the universe, I mean.
Uh, Hold on. Determine in years the age of the universe when the light detected was originally at the. Actually, it's a combination of both.
Mm.
Okay. Let me see.
Is the light part the second equation?
Yeah.
Okay.
Okay. Now, again, when you use the second formula, you need the redshift, right?
0.13
The 0.13. And what's that equal to? And what does that mean? So z equals
equals
0.13, and that's equal to
um some r over 1 minus 1.
r over r0 minus 1, right?
Oh.
Okay.
Also, when the universe grows,
Mm-hmm.
does gets big or expands,
Yeah.
does the rate it grow increase?
Um, yeah, it does. It,
Hmm.
but here's the thing, that's a relatively recent discovery.
Hmm.
Um, we discovered that okay, the universe is expanding according when Edwin Hubble came up with it. And Edwin Hubble kind of did that in the 1950s if I'm not mistaken.
Mhm.
Okay. But he assumed that the rate of expansion was constant. Okay.
Hmm.
However, in mid 1990s, several astronomers actually got data that suggested that the universe was not only expanding, but it the expansion accelerates. It was
Hmm.
expanding. It's expanding faster now than it was 10 years ago, and it's actually
Wait,
measurable.
so the explosion is still happening or what?
Sort of. Now the thing about this, and this is the interesting bit here. This kind of says this kind of says that, well, let's not go there first. If you think about it, if the only force that acts on the universe as a whole is gravity, because the other forces are either too short ranged or doesn't affect mass, right? In the scale
Mhm.
of the universe, it's only gravity. We can assume it's gravity only, right? But think about
Mhm.
it this way: if gravity was the only force, then it shouldn't. It may keep expanding, but it should slow down and eventually either stop or come back onto itself, right?
Mhm.
So the observation that the universe was actually, instead of slowing down, it was speeding up its expansion. Uh, the consequence, no, not the consequence. The only possible explanation for that is there's another force that opposes gravity at large scales. Okay,
Mhm.
and we call that force right now dark energy because we don't know exactly what it is, but we call it dark energy for now. We have not found out since the mid 1990s what dark energy actually is.
Mhm.
Okay. All right. So going back to the question for B. So this is correct. So you said that R0, one of those R's will become 1, right? just to make it
Mm-hmm.
easier. Now, I wouldn't personally change it to 1 for now. I'm just gonna have to write this as r over r0, right, is equal to 1.13. Okay. Now, there's a particular thing here that you need to do to kind of see what's happening, but uh, okay. Well, we'll just do it. We'll just
But
keep
that
it like that.
means
hmm
R is bigger than RO.
R is bigger than RO. In other words, the current size of the universe,
Is
is 1.13 times the size of the universe when the light was emitted.
oh, that's big.
Okay. So right now it's 13% bigger. It's not correct to say
Mm-hmm.
that going back is 13% smaller though. Okay. It's not correct to say that.
Mm-hmm.
You have to say that now it's bigger by 13%. Now, having said that, um, okay. Where is that? Gives Yeah, determine the years, the age of the universe. Okay, here's the thing. We know that the age of the universe now, right? The age of the universe now is 13.4 times 10 to the 9 years. 13.4 times 10 to the 9 years, right?
Mm-hmm.
Okay. Remember, the now is bigger, so that should be that. Now, this should be the same, this ratio should be the same as the time for the age of the universe back then. Okay. Uh, I think you may not quite get what I meant by that. Over T0. Okay. Um, but this is gonna be the idea, and this is gonna be where you finish it off. So T0 is equal to 13.4 times 10 to the 9 divided by 1.13.
So did you just replace the Hubble constant with? Oh no, there's a
No,
weird
no,
bug.
no, okay. I think I'll tell you why this is the case, okay? Remember that it's assumed that the universe is expanding at a certain rate. In other words, it's got a speed of expansion, right? Okay,
Mm-hmm.
I'll just write the answer here first. So the correct answer is 11.9 times 10 to the 9 years. Okay? Um okay, I'm going to explain why this is the case. Remember that the speed of expansion is constant, right?
Mm-hmm.
Constant. And
So is the
also,
and Hubble also increases.
mhm. So in this case, because of the speed of expand, no, the Hubble thing, no, because it's assumed that this is constant throughout the age of the universe for this problem.
Mm-hmm.
Okay. So anyway, and the thing is, we know the formula for speed. That's distance over time, right?
Mm-hmm.
Right. So if you think about it, this distance could be the r, and this time could be the t, the age, right? So that means r0 over t0 is equal to r over t, right?
Yeah.
And then we're just gonna rewrite this into something more familiar, r0 or r over r0. And what happens? You just put that there. You just cross multiply these, t over t0, and that's where we get this.
So T is R over R0.
T over t0 equals r over r0.
Okay, wait, let me write.
Okay.
So wait, is Hubble constant written as H0 or HD?
H0, H0.
Okay. Um, so you said T over T0 is
Mm-hmm.
equal to R over R0?
Mm-hmm. Again,
Mm-hmm.
this, just so we're clear, this comes from this. And this comes from the fact that the speed of expansion is constant and it's equal to distance over time. The distance is r, the time is the age.
Mm-hmm. But
Okay.
then if you, but then where does the Hubble constant go? Where does the value go?
We don't need it in this problem. We don't need it.
So what happened?
Nothing. It's a distractor.
Oh no, like oh you just
Yeah. Actually, if you want to use the Hubble constant here, you could, but it's gonna be a longer solution. So I just avoided the longer solution.
no. But how do you know if that it's t 0 or whatever 13.4 billion?
No. The idea here is okay. Let's zoom back in there. The idea
No, no,
here,
no. Oh, you said RO
yes,
is TO.
yeah. This particular bit you're saying means if you use this value for a Hubble constant into this equation, the t equals 1 over h0, you will get an age of the universe of 13.4.
Mm-hmm.
Okay. So that's again, if you use that Hubble constant there, you'll get that age. In other words, if you read the question carefully, you don't actually need to know what the Hubble constant is for this bit anymore. You just need to know that the age of the universe is 13.4
Mm-hmm.
times 10 to the 9 years. Okay. 13.4 billion years. All right. Last question. Evidence based on observations on type 1a supernovae affect the results in B1. What is the relevant conclusion from these observations? We just talked about it. That's the answer. We just talked about the answer.
Wait. Um. mm,
Okay, I'll give you a clue. Even though we just talked about it, here's the clue.
so I was still writing the answer like
All right,
before.
you're still
Wait.
writing. All
So
right, sorry.
11.9 times 10 to the 9 is TO, right?
Yes.
Okay. 0.9.
Mhm.
Okay. That's the age now.
No, that 11.9, the age now is 13.4. The light was emitted
Oh,
at the age of
age then.
11, at the age of 11.9. So in other words, it took around, I don't know, 2.5 billion years for the light to travel.
Okay. So when the light was emitted.
When the light was emitted to when it got here, took around 2.5 billion years.
Hmm.
Okay.
Okay. We're
All
okay.
right. So let's do the last question and then we can end for the night.
Mhm.
All right. So evidence based on the observation of type 1a supernovae affect the results in B1. State the relevant conclusion of these observations.
Wow. I totally forgot about the 1A stuff.
Okay. Um it's only one mark, so you don't have to go all the way there.
I'll just say something.
Uh-huh.
Uh, could it just be what we just said?
Yeah, what
Like, it takes a long time for light to travel.
mm-hmm. Somewhat related to that. But
Oh,
okay,
oh.
go ahead.
Um, the the age of the universe. No, no. Light takes. Okay, light takes approximately 2.5 billion years
Mm-hmm.
for the Earth to detect it.
No, not quite. And that 2.5 billion years is only for this particular was it a galaxy? Yeah, particular galaxy. But it's
Mhm.
not true for all galaxies.
Mhm.
Okay. Give you one clue. Okay. We just talked about it. Is the universe expanding evenly or not? or uniformly
Oh
or not?
no, not
No, it's
uniform.
not. How do we know it's not expanding uniformly?
Because the red shift changes.
Hmm.
No, the Hubble constant changes.
But why does it change? Okay. Um, okay, I gotta consult Mark's scheme here because there are many possible answers to this. So the Mark scheme will just clarify what they're trying to look for. All right. Okay, got it. Remember, it's only one mark. No need to overcomplicate it. Okay. Okay, I'll give you something. We've already talked about the fact that the universe is not only expanding, but it's accelerating in its expansion, right?
Hmm.
How do we know from type 1a supernova that happens?
I don't even know what Type 1A supernova is.
Oh, I if okay. The idea here is I'll just tell you first. Type 1a supernovas are a standard candle.
What's that mean?
Okay. As type 1a supernova first occurs when you have a white dwarf orbiting, or you have two stars orbiting each other. One of them is a white dwarf. Okay. Now, what happens because the white dwarfs are tiny? That means its gravity is relatively strong, right? So it pulls material from the other star into itself.
Wait, so do they become black holes eventually?
No, they don't. What happens is
Okay.
what happens is the red giants when they go supernova, that's a type 2 supernova.
Mm.
Okay, type 1a is the white dwarf getting all that material from the exostar. Now remember from white dwarfs, what happens? The white dwarfs themselves are around one solar mass to start with, right? But what
Hmm.
happens as they accumulate, as they get material from the other star?
Their
The
mass
Their
increases.
mass increases until it reaches the Chandrasekhar limit.
Yes.
Once the Chandrasekhar limit is reached, we get a helium flash. Or not a helium flash. We get a flash. All the hydrogen starts fusing. Boom. So here's the thing. Once it doesn't matter what kind of white dwarf you have, right? As long as it gets material and it reaches a Chandrasekhar limit, it's gonna go boom. So every type 1a supernova goes boom at the Chandrasekhar limit, right? Makes
Hmm.
sense, right? Now, because they
Hmm.
always go boom at the Chandrasekhar limit, that means they always have the same brightness, no matter where they are in the universe.
Seriously.
Yes. So, of course, the farther something is, and you know that it's a type 1a supernova, then you would observe, if you know it's a type 1a supernova, it's going to be dim, but you know how bright it should be. And then you can calculate basically how far it is, right?
Hmm.
You get the idea? So, the farther the type 1a supernova is, you can still identify it as a type 1a supernova because it's a sudden flash of light in the night sky. Okay. All you have to do now is determine whether it's type 1a, type 1b, or type 2. We haven't learned type 2b because it's not important for IB physics. The only important ones for IB physics are type 1a and type 2. Okay.
Hmm.
So anyway, the idea here is because they're standard candles, they're always the same brightness. That means if you observe a type 1a supernova, you can determine how far it is, right? And if you can determine how far it is, you can also determine how fast it's going, more or less, right?
Hmm.
Now, the key
But isn't the
idea,
brightness the same everywhere?
the brightness is gonna be the same everywhere, and also, you can look at the red shift of the spectral lines, so you can determine how fast it's moving as well, right?
Hmm.
Okay, so once you combine that information of how fast it's moving and how far it is, and then you put that into the Hubble equation, the Hubble constant has changed every year since 1995 when we first discovered the effect. Again, the Hubble constant has changed every year by a small amount, but it does change. Okay.
Mm-hmm.
All right. So these observations of type 1a supernovas have revealed that the universe, so basically we're going to the shortcut. The type 1a supernovas have revealed how fast the universe is expanding and that the expansion is also accelerating. So that is our answer here. Okay.
Mm-hmm.
So I'll just write down the answer here before we end. Okay. So, okay. I'll just write it in terms of, I'm trying to get all the marks, so I'll write some relevant information as well. Okay. So I'm gonna write here type 1a supernova. Sorry, 1a supernovae are standard candles, which help determine the speed and distance of the event, right? Of let's say its galaxy. I'll just say it in this case in galaxy. Okay. So that's the first thing I'm gonna write, and then the second thing I'm gonna write here is um discovery. Okay, so discoveries from continuous measurement of these supernova measurements of these uh supernovae have revealed that the universe expansion is accelerating.
Um,
And this is
can
the
I
answer.
write? That's like 5 marks.
Yeah, I know. Um the the one mark here is this.
Can I say type 1A supernova reveals how fast the universe is growing?
No, not just how fast, but you have to say that it's expanding. That the expansion is
Well,
accelerating. Okay.
okay. How much the unit? Wait, what? Reveals the acceleration of the universe's expansion.
Mm-hmm. Yeah, that's good.
Mm-hmm.
All right. All right. So yeah, that's the end of that. So paper three. I really feel like paper three is the hardest one to discuss because of so many things you need to cover.
Mm-hmm.
The others are kind of fast ones. We just go through the idea and done, right?
Mm-hmm.
Okay. So next, so tomorrow, paper two. Oh no, paper one. Yeah, tomorrow.
Yeah. Yes.
All right. Okay. Anything else you'd like to ask before we end for today?
No. That's good.
No. All right. So great. So good to know that you learned something.
A lot at
Uh,
least.
right. Especially in astrophysics, I hope, because I'm pretty sure
Yeah.
you didn't have enough time to cover everything.
Nah, very not.
Yeah. All right then. So, all right. So we'll end it here today. I'll see you again tomorrow. Okay. Have a
Okay.
good night,
Thank you.
CJ. Bye bye now.
You too. Bye.
Okay. Uh, so that's the end of the stream. Thank you, CJ, for that. Whoa, 3 hour stream. Haven't had one like that before. All right. So let's just, before we end, oops, sorry. Okay, let me just see if anyone else has submitted anything. Nope. Okay. So again, yeah. So with, again, I keep saying this at the end of every physics lesson. So again, it doesn't matter which flavor you're taking. You're basically learning the same things over and over again across the different brands of schooling that you could have. So IB, Cambridge based, SATs. If you're in the US, you're probably gonna be doing either what's the term here? AP physics or standard physics. Okay. Again, it doesn't matter where we are, what brand you're doing. What matters is it's the same knowledge over and over again. It's just the way the questions are presented in the exams usually and the way that the assessments are done. But in terms of content, all the same. Why? Because my physics is the same as your physics and it's the same as everybody's physics. Okay. Anyway, so I hope for those who are still in the stream, I hope this person, what's his name? Catio. Okay. Yeah, I hope you're still in the stream. If not, yeah, just thanks for joining earlier. And yeah, I wish all those test takers wherever you are again, whether it's again, whether it's IB, Cambridge based, GCSE, uh, SAT, whatever, because I know it's exam season for a lot of different schools right now. So good luck with everyone, and I hope this helps. So we'll end the stream here today. So before we do, don't forget, oops, I changed the text. I forgot. I forgot that I changed that text. Okay. Again, don't forget to like, share, and subscribe to all the uh, what's this? All the social media platforms. I'm most active definitely on YouTube or not Facebook on YouTube. Okay, so mm, okay, so don't forget to like, share, and subscribe to the channel. And with that, we can end today's stream. So good. So hold on, I'll just adjust this. All right. Okay. So with that, good day, good morning, good evening, good afternoon, good night, wherever you are in the world. And don't forget to stay freaky, everyone. Take care and bye bye now.